On February 14, 2021, the temperature in Dallas, Texas fell to -18 degrees Celsius. This sentence should not be possible. Dallas sits at 32 degrees north latitude, the same latitude as Casablanca, Morocco, Rabat, Fez, the Saharan margin. It is a city built for heat, for sustained triple-digit summers, and for mild winters. Its water pipes, electrical generation system, roads, and building standards were designed from the historical record of what Dallas winters had been. -18 degrees Celsius was not in that record. Over the following week, 4.5 million Texas households lost power. Some lost it for hours. Others lost it for days, through the coldest nights the state had experienced in recorded history. Gas lines and water pipes froze and burst in cascading failures that engineers had not modeled because those conditions had not appeared in the historical data used to set design standards. 246 people died. Many died of hypothermia. Others died from carbon monoxide poisoning caused by improvised heating. Still others died in medical emergencies that could not be reached through frozen roads or treated in hospitals operating on generators. The economic damage exceeded $200 billion. Water damage from burst pipes alone was estimated at $15 billion. It became the most costly winter weather event in United States history. The political conversation focused on the electrical grid, why it was not winterized, who was responsible, and whether deregulation had encouraged underinvestment in resilience. Those were legitimate questions. But they were not the most important question. The question almost nobody asked was this: why was Arctic air in Texas? Arctic air does not normally reach Texas. The physical mechanism that normally prevents it is the polar vortex, a planetary-scale atmospheric circulation, a swirling mass of extremely cold air covering the Arctic region and contained within polar latitudes by the temperature gradient between the frigid Arctic and warmer mid-latitudes. When the vortex is coherent, that gradient creates a pressure boundary. Arctic air stays inside it. The mid-latitudes stay outside. The February 2021 event was a sudden stratospheric warming. Rapid heating high above the Arctic disrupted the vortex. It fragmented, and lobes of Arctic air pushed south. One moved through Canada and the American Midwest. Another reached Texas, Oklahoma, Arkansas, and Louisiana. The conventional explanation is Arctic amplification. As the Arctic warms disproportionately from greenhouse gas accumulation, the temperature gradient narrows. A narrower gradient means a weaker boundary, a vortex more prone to disruption, and more events like Texas 2021. This explanation is physically sound. Arctic warming is real, the gradient has narrowed, and the vortex has become less stable. But the hidden axis identifies another detail. These disruptions are not occurring uniformly around the Arctic margin. They are increasing in specific longitude sectors. The sector showing the greatest increase is the one the North Magnetic Pole has been vacating as it accelerates toward Russia. The book proposes that the polar vortex is organized around the magnetic North Pole and that an electromagnetic framework centered on the magnetic axis partially governs where coherence is strongest and where disruptions most easily propagate southward. As the magnetic pole moves away from the Canadian Arctic, the North American longitude sector weakens. In this framework, Texas 2021 was both things simultaneously. Arctic warming weakened the vortex overall, while magnetic pole departure weakened it specifically in the North American sector. The question connecting them, why coherence is failing in that sector on a timeline paralleling the pole's departure from Canada, is the question the book sets out to answer. Texas was the most dramatic domestic expression of a pattern already building. Europe endured an unusual cold outbreak in February 2012. In January 2014, temperatures in parts of the American Midwest fell to -40 degrees Fahrenheit, bringing the phrase polar vortex into popular conversation. In February 2018, Eastern North America and Europe experienced simultaneous disruption as parts of the Arctic warmed toward freezing. Then came Texas in 2021, record cold in Japan and South Korea in 2023, and unusual European cold in 2024 while the Arctic was anomalously warm. The book identifies a shift in the longitude of expression, toward the East Asian and North American sectors, and away from European longitudes that dominated the historical record. That shift, the book argues, is the magnetic pole signature. The pole has moved from Canada toward Russia. The vortex's organizing center has moved with it. Sectors the pole is vacating become more prone to disruption. The Russian and Siberian sector the pole is approaching experiences stronger coherence as the organizing influence concentrates there. The framework generates a prediction that atmospheric data can test. The signal is described as real but noisy, with more years needed to separate it from natural variability. Yet its direction is consistent with the electromagnetic organizing framework the book proposes. And the polar vortex is only one expression of the larger pattern. Southern Australia has lost cool season rainfall while Northern Australia has received more. Greenland has lost ice rapidly since the mid-1990s, concentrated in specific sectors. West Antarctica has lost ice while East Antarctica has remained approximately stable. The North Magnetic Pole has moved 2,200 kilometers from its 1831 position. The South Magnetic Pole has left Antarctica and is drifting toward Australia. Both are moving away from the frozen land masses at Earth's polar regions. The hidden axis proposes that these are not disconnected events. They are expressions of one planetary system in transition. On the first day of June, 1831, British naval officer James Clark Ross stepped onto a frozen peninsula in the Canadian Arctic and watched his compass needle point straight down into the ice. Ross had been searching for the point where Earth's magnetic field lines converge and enter the ground vertically. On the Boothia Peninsula, at 70 degrees, 5 minutes north and 96 degrees, 46 minutes west, he found it. He planted a flag. That flag, if it could still be standing, would now be more than 2,200 kilometers from the magnetic point it marked. The land beneath it did not travel. The North Magnetic Pole did. It crossed the geographic North Pole and entered the Russian hemisphere. It is still moving. The science did not begin with Ross. It began with navigators. From the 16th century onward, officers recorded the difference between true north and the direction their compasses pointed, a difference called magnetic declination. It was not merely an inconvenience. It was a navigational hazard. Voyage after voyage, year after year, the records accumulated. Scientists later used thousands of ships' log entries to reconstruct the field from approximately 1590 to the present. The reconstruction revealed that the poles had always moved, but for centuries the North Pole wandered slowly, averaging roughly 10 kilometers per year. Ross gave science a precisely located point. Roald Amundsen found that it had moved by 1904. Canadian survey teams followed it through the 20th century as it traveled north and northwest through the high Arctic. Then came the acceleration. From 1831 to about 1970, the pole traveled roughly 1,100 kilometers in 139 years. From 1970 to 2025, it traveled another 1,100 kilometers in only 55 years, and the rate at the end was still increasing. The acceleration is the story. By the early 2000s, the North Magnetic Pole was moving between 55 and 60 kilometers each year, more than 5 times its historical average. In 2019, its position diverged so far from the World Magnetic Model, the international standard used by aircraft, ships, GPS systems, and navigation charts, that an emergency correction was required 1 year before the scheduled update. This had never happened before in the model's history. As of 2025, the pole sits at approximately 85.7 degrees north and 139.3 degrees east. It has crossed the geographic North Pole, entered the Russian hemisphere, and traveled more than 2,200 kilometers from Ross's flag. To understand the movement, we must understand what a magnetic pole is. It is not a physical object. It is the location where the planet's magnetic field enters the surface vertically. Stand there with a dip needle and it points straight down. The field is generated in Earth's outer core, a layer of liquid iron and nickel about 2,200 kilometers thick surrounding the solid inner core. Temperatures rise from about 4,000 degrees Celsius at its outer boundary to about 6,000 degrees near the inner core. The conductive liquid is in constant turbulent motion, driven by heat and organized by Earth's rotation. That movement creates electrical currents. The currents generate a magnetic field. This self-sustaining process, the geodynamo, has operated for at least 3.5 billion years. Earth's field is not the clean, symmetrical field of a bar magnet. It contains lobes, reversed flux patches, and variations across time. Two large magnetic lobes in the outer core, one beneath Canada and one beneath Siberia, compete for dominance. The Siberian lobe has been gaining influence. As the balance shifts, the pole migrates toward Siberia. The exact dynamics driving that change remain under active study. The result is established: the pole has moved into territory it has never occupied during reliable human measurement. The North Magnetic Pole receives most of the attention. But the Southern Pole tells an equally significant story. On January 16, 1909, Edgeworth David, Douglas Mawson, and Alastair Mackay completed a punishing 1,200-mile journey from Ernest Shackleton's Antarctic base. They man-hauled sledges across crevassed ice fields and through storms. Near 72.25 degrees south and 155.1-5 degrees east, their dip needle pointed vertically. They planted a flag. The South Magnetic Pole is no longer on the Antarctic continent. It moved offshore during the 1950s. By 2000 it was far into the Southern Ocean. In 2025 it sits at approximately 63.9 degrees south and 135.1 degrees east, open water between Antarctica and Australia, drifting northwest at roughly 10 to 15 kilometers per year. Its direction is geographically significant. The South Magnetic Pole is moving toward Australia. Hold both facts together. The North Magnetic Pole has left Canada and is moving toward Russia. The South Magnetic Pole has left Antarctica and is moving toward Australia. Both departures continue. Both accelerated during the late 20th and early 21st centuries. Both poles are moving away from the frozen landmasses of Earth's polar regions. The book presents this as one planetary magnetic system in coordinated transition. The magnetic axis, the line joining both poles through Earth's center, is changing its orientation relative to the surface. Both ends are moving at the same time. In December 2025, scientists at the British Geological Survey noted a configuration that may not have occurred in centuries. The North and South magnetic poles briefly shared the same longitude, 135 degrees east. At opposite ends of the Earth, both poles aligned on the same meridian. Something is happening to the system as a whole. News coverage treats pole migration mainly as a navigation problem. Airports update runway headings. Ships recalibrate charts. Phones update magnetic models. Those consequences are real. But the book argues they are the smallest consequences. Earth's magnetic field is the organizing framework of the planet's electromagnetic environment. It determines where cosmic rays penetrate the atmosphere, where auroral zones concentrate energetic particles, how electrical currents are organized in the upper atmosphere, and how energy from the solar wind couples into the magnetosphere. The field extends far into space, forming an asymmetric bubble called the magnetosphere. It deflects the solar wind and cosmic rays streaming toward Earth. Without it, the atmosphere would be slowly eroded, as happened to Mars after that planet lost its global magnetic field. The magnetosphere is not uniform. The South Atlantic anomaly is an expanding, deepening region of locally weaker field over the South Atlantic and part of South America. Satellites passing through it experience increased radiation anomalies. The book connects its expansion to the movement of the South Magnetic Pole and the weakening of the geomagnetic field since the 1840s. The auroras are the visible expression of this electromagnetic coupling. Charged particles travel along field lines and collide with molecules in the upper atmosphere. The light occurs in geographic bands, the auroral ovals, centered on the magnetic poles. As the poles move, the ovals move. The book proposes that the zone of maximum electromagnetic energy input shifts with them, and that atmospheric systems organized around this framework, the polar vortex, jet streams, and stratospheric circulation, shift in response. The biological world carries another possible record. Sea turtles, migratory birds, salmon, honeybees, and some bacteria navigate by sensing the magnetic field. The book notes disruptions in migration, strandings, and nesting patterns as indicators consistent with a changing electromagnetic environment, while recognizing that other factors may contribute. What moves with the poles may extend far beyond the compass needle. In February 2002, two NASA satellites began measuring something never measured this way before, the precise mass of Greenland's ice sheet, updated monthly from space. The Gravity Recovery and Climate Experiment, GRACE, tracked the distance between two satellites flying 220 kilometers apart. As they passed above regions of different mass, gravity altered the gap between them by as little as 1 micrometer. From those tiny changes, scientists calculated the movement of oceans, land, and ice. It was a scale for weighing a continent. The Greenland signal was not subtle. The sheet lost mass month after month, year after year. When the original GRACE mission ended in 2017, it had recorded 181 consecutive months of net ice loss. GRACE follow-on continued the record. The book gives an average loss of 264 gigatons per year. In 2019, Greenland lost 532 gigatons, enough in that year alone to raise global sea level by 1.5 millimeters. Arctic warming, running at roughly 3 times the global average, is genuinely driving Greenland ice loss. But the book asks where, precisely, the ice is disappearing. The greatest loss is concentrated in specific coastal sectors. The southeastern coast, facing the open North Atlantic and oriented away from the Canadian Arctic where the magnetic pole had been, shows the most dramatic sustained loss. The northwest also loses heavily. The northeast, facing the Russian sector toward which the pole is moving, shows comparative stability. The interior dome thins but holds. The hidden axis identifies a directional pattern, ice is leaving where the magnetic pole has been and holding where it is going. It states openly that this is a framework inference drawn by comparing GRACE geography with pole trajectory. The GRACE mass distribution is the measurement. The proposed magnetic connection is the framework's contribution. The mechanism proposed runs through the atmosphere. As the electromagnetic organizing framework moves, precipitation and melt patterns shift with it. The bilateral pattern appears again in Antarctica. The continent holds approximately 26.5 million cubic kilometers of ice, divided principally between the West Antarctic ice sheet, the East Antarctic ice sheet, and the Antarctic Peninsula. The regions behave very differently. West Antarctica is losing ice at approximately 138 gigatons per year, with the rate accelerating. Much of its bedrock lies below sea level. Warm circumpolar deep water reaches beneath floating ice shelves, melting them from below and destabilizing the glaciers behind them. Thwaites Glacier is among the most rapidly changing ice masses on Earth. East Antarctica, the largest single body of ice on the planet, is approximately stable. In some periods it gains slight mass through snowfall. While much of the cryosphere accelerates its loss, East Antarctica holds. The South Magnetic Pole spent the early 20th century in the East Antarctic sector. As it moved northwest, off the continent and toward the Australian sector of the Southern Ocean, West Antarctica entered accelerating ice loss. East Antarctica remained stable. The book reads this as the southern half of a bilateral pattern. 2 poles. 2 ice sheets. Both poles moving away from their polar landmasses. Both ice sheets losing ice in the sectors associated with departure, while other sectors remain comparatively stable. The timeline provides a third line of evidence. Greenland shifted from approximate balance to net loss in the mid-1990s. The North Magnetic Pole's rapid departure from its historical baseline also developed chiefly from the 1990s onward. The South Pole's northwestward drift runs alongside West Antarctica's sustained loss. The manuscript does not claim that timing alone proves causation. It notes rising greenhouse gases and shifting ocean currents as simultaneous factors. But it argues that the bilateral movement and bilateral ice pattern are sufficiently precise to demand a direct test, analyze atmospheric circulation in those sectors as a function of magnetic pole position while controlling for greenhouse forcing. The framework's answer is causal. The test is waiting to be performed. The ice leaving Greenland and West Antarctica does more than raise the sea. It changes the land beneath it. Every gigaton of ice is a gigaton of mass that pressed downward on bedrock for thousands of years. Remove that mass and the crust rises. This process, isostatic rebound, is the geological system responding to ice redistribution. In the most active areas of West Antarctica, bedrock is rising at documented rates of 40 to 50 millimeters per year, faster than almost anywhere on Earth. Beneath Iceland's Vatnajökull ice cap, the land is rising by roughly 20 millimeters per year. The hidden axis follows a cascade. Atmospheric reorganization changes the distribution of ice redistribution changes the load on the crust and mantle respond to the changing pressure. Later episodes will trace that cascade into volcanic and seismic systems. For now, the importance is immediate. The ice is disappearing in geographic patterns. Those patterns are already producing specific geological responses in specific places. Atmosphere, cryosphere, and geosphere are linked in a process that is visible in the present tense. The book's case rests on 3 elements: geographic specificity, bilateral symmetry, and timeline correspondence. Ice loss is concentrated rather than uniform. A related directional pattern appears in both hemispheres. And its acceleration parallels the modern movement of the magnetic poles. But the clearest current expression of the proposed atmospheric reorganization is not found on an ice sheet. It appears on a continent with no ice sheet at all, where the shift can be read in 60 years of rain gauge records. The continent is Australia. The pattern is a split, the south drying while the north becomes wetter. In December 1965, the Australian Bureau of Meteorology installed a rain gauge at a research station in the Kimberley region of northwestern Australia. Graph its readings today against that baseline and the line trends upward. The Kimberley has become approximately 40% wetter. 3,000 kilometers south, in Western Australia's wheat belt, another graph moves in the opposite direction. Cool season rainfall, the water supporting grain, cities, and the landscape's productive capacity, has fallen for 50 years. The current average is roughly 20% below the 1970 baseline. Same continent. Same period. Same atmospheric system. One half 40% wetter. The other half 20% drier. The southern decline appears throughout the systems that depend on rain. Since 1997, inflows to the Murray-Darling Basin have averaged approximately 38% below the long-term average. The basin supports the agricultural heartland of southeastern Australia and produces about 40% of the country's agricultural output. Perth's winter rainfall has declined by approximately 20% since the 1970s. Its groundwater is depleted. A city of 2 million now receives most of its drinking water from desalination plants. In the wheat belt, the viable farming margin is shifting as the southern edge becomes too dry for reliable production. The atmospheric mechanism is the southern annular mode, or SAM. When the pressure difference between the middle latitudes and Antarctica increases, the westerly wind belt contracts toward the pole, carrying rain-bearing storms away from southern Australia. The SAM has reached its most persistently positive state in 1,000 years. The consensus explanation identifies greenhouse warming and ozone effects. The hidden axis proposes a third driver, the south magnetic pole's approach toward the Australian sector, reorganizing the electromagnetic framework that partially organizes the SAM. While the south dries, northern Australia tells the other half of the story. Northern Australia's transformation is less discussed, but its magnitude is greater. The Kimberley's 40% rainfall increase since the 1960s is changing the landscape. Seasonal rivers become perennial. Floodplains inundate more reliably. Tropical vegetation advances into areas once too dry to support it. The Northern Territory has endured exceptional wet seasons that overwhelm infrastructure designed for the historical rainfall regime. Queensland's 2010 and 2011 floods inundated an area larger than France and Germany combined, caused approximately $30 billion in damage, and killed 35 people. Major floods followed with a frequency that turned the exceptional into the expected. The immediate mechanism is an intensifying Australian monsoon. Moist tropical air is drawn south during the wet season with greater frequency and intensity. The book presents one force producing two opposite effects. The westerly storm tracks contract away from the south as tropical monsoon circulation strengthens in the north. That is the bilateral signature. The hidden axis predicts that the SAM's positive trend will persist and deepen as the south magnetic pole continues its northwestward approach. It also gives a falsification condition. If the SAM trend reverses as ozone recovery proceeds, the proposed electromagnetic driver is weakened. If the trend continues despite ozone recovery, the driver gains support. The test is ongoing. Australia matters because it is the clearest present-day example of what the book identifies as the atmospheric signature of magnetic pole approach, bilateral continental reorganization, producing opposite effects at different latitudes at the same time. The first section of the investigation is complete. Texas showed the question. Ross's flag established the measurement. Greenland and Antarctica reveal the directional pattern in the ice. Australia revealed the same bilateral organization in rainfall. A continent split in two. One half drying under structural stress. The other flooding as its landscape is transformed. The same continent. The same atmospheric system. The same cause, the book argues, expressed in opposite directions because the south magnetic pole is approaching from below. The next episode enters the planetary mechanism. The axis has been measured. Now it must be Everything described so far has a conventional explanation. The magnetic poles move because of fluid dynamics in the outer core. Ice melts because of atmospheric warming. Australia reorganizes because the southern annular mode shifts under greenhouse forcing and ozone effects. These explanations are true. The framework of the hidden axis does not replace them. It sits beneath them. Conventional explanations describe what happens at Earth's surface. They share an assumption: the surface is the stable reference frame. Poles move relative to the surface. Ice melts on the surface. Weather operates above the surface. The crust is treated as the fixed canvas on which planetary events are painted. But what if the surface is not the most stable thing in the system? In 1905, Albert Einstein changed how physics understood motion by showing that observations depend on the reference frame from which they are made. A person on a train and a person watching from the platform describe the same event differently, and both descriptions can be correct within their frames. Geophysicists measure magnetic pole movement against latitude and longitude on Earth's crust. When they say the north magnetic pole moved 2,200 kilometers, they mean it moved relative to that surface grid. But the magnetic field is generated 2,900 kilometers below the surface, in liquid metal that has its own dynamics and angular velocity. The sun does not interact with a latitude grid. The solar wind encounters the magnetic structure generated in Earth's core. The book therefore proposes a more fundamental reference frame: the magnetic axis, the line joining the magnetic poles through the center of Earth. From that frame, the question inverts. Not, where is the magnetic pole moving across the surface? But, where is the surface moving relative to the magnetic axis? That inversion is the conceptual foundation of the deeper framework. The idea that Earth's surface can migrate relative to its deeper interior is not speculative. Geophysics calls it true polar wander. True polar wander, or TPW, describes rotation of Earth's solid outer layers, the lithosphere and upper mantle, relative to the spin axis and deeper interior. Like any rotating body, Earth tends to orient so its spin axis passes through its maximum moment of inertia, the direction where mass is most concentrated. When mass is redistributed through growing or melting ice sheets, mountain building, or movement in the mantle, the outer planet readjusts toward a new equilibrium. Picture a raw egg spinning on a table. If the denser yolk shifts, the egg wobbles and reorients because its mass has moved relative to the spin axis. Earth responds on geological scales. Continents, ice sheets, mountains, and ocean basins alter the planet's mass distribution. When that distribution changes, the outer shell reorients. Paleomagnetic signatures frozen into ancient rocks preserve the direction of the field when those rocks formed. By reading those natural compasses across continents and ages, geophysicists reconstruct the surface's position relative to the spin axis over billions of years. The record shows repeated, significant movement. The manuscript describes an Ediacaran event about 800 million years ago in which Earth's outer layers may have rotated by as much as 50 degrees. Smaller events appear in the Cretaceous and Cenozoic records. Satellite measurements show that polar drift continues today. The book cites research finding that its direction shifted around the year 2000 and proposing accelerated ice melt, especially in Greenland and West Antarctica, as the primary driver. True polar wander is confirmed science. Ice mass redistribution can drive surface migration relative to the rotation axis. The hidden axis extends that principle into the electromagnetic domain. Just as the surface migrates relative to the spin axis, the framework proposes that it migrates relative to the magnetic axis, and that atmospheric organizing systems respond to that changing relationship. The magnetic axis originates in the geodynamo, operating from 2,900 to 5,150 kilometers beneath the surface. Earth's liquid outer core is approximately 2,200 kilometers thick. Temperatures range from roughly 4,000 degrees Celsius at its outer boundary to about 6,000 degrees near the inner core. The metal is about 11 times denser than water and is in constant turbulent motion, driven by heat and organized by planetary rotation. Moving conductive liquid generates electrical currents. Those currents generate a magnetic field. The existing field helps sustain the currents that regenerate it. This self-sustaining geodynamo has operated, through interruptions and reversals, for about 3.5 billion years. The instantaneous field is complex, lobes, reversed flux patches, and secular variations evolving over years to millennia. Yet across tens of thousands of years, its dominant form is a geocentric axial dipole, organized mainly along the rotation axis with the magnetic poles averaging near the geographic poles. The long-term alignment is not accidental. Rotation and the Coriolis effect organize convection in ways that favor an axial dipole. The magnetic axis is coupled to the rotation axis by rotating fluid dynamics. The rotation axis, in turn, is coupled to the solar system's angular momentum. For the framework, this means the magnetic axis wanders in the short term but remains constrained over the longer cycles relevant to grand solar minimums. It is not absolutely fixed. Poles wander. Excursions occur. Reversals happen. But the book argues it is stable enough relative to the Sun for surface migration around that framework to have measurable atmospheric consequences. The surface is not a stationary stage. The outer core is not a silent background. Between them is a moving relationship, and above them is the solar environment that meets the field before it meets the world where people live. The next link is electromagnetic coupling, how energy from the Sun enters the magnetic system and reaches the atmosphere. The solar wind carries more than particles. Embedded within it is the interplanetary magnetic field, or IMF, continuously interacting with Earth's magnetosphere. When the interplanetary field is oriented opposite to Earth's field at the magnetopause, magnetic reconnection can occur. Field lines break and reconnect across the boundary, allowing solar wind energy, particles, and magnetic flux to enter the magnetosphere. Reconnection is the primary pathway by which solar wind energy reaches Earth's upper atmosphere. It drives auroral currents, heats the polar thermosphere, and moves plasma through the magnetosphere. Solar flares, coronal mass ejections, and ordinary variations in solar wind become part of Earth's electromagnetic environment through this process. The geometry of reconnection depends on the orientation and configuration of Earth's field. As the magnetic poles move and field geometry changes, the book argues that the pattern of energy deposition changes with it. The auroral ovals are the visible expression, rings of electromagnetic activity centered on the magnetic poles. As the poles move, the ovals move. Regions receiving maximum upper atmosphere energy input shift as well. The least understood link is the passage from ionosphere to troposphere, the lower atmosphere where weather occurs. The manuscript identifies electric field coupling, particle precipitation that changes atmospheric chemistry, and thermal effects from auroral heating propagating downward through the stratosphere. It states that the magnitude relative to ordinary thermal forcing is debated, while maintaining that the physical coupling exists. The framework's mechanism is precise. Pole movement shifts the electromagnetic framework of the upper atmosphere. Energy deposition patterns shift. Circulation organized partly around that framework changes its longitude of expression. During grand solar minimum conditions, weakened solar electromagnetic coupling amplifies coherence loss in zones corresponding to the pole's new position. The chain is complex and partly understood, but the book presents every link as physical: solar wind to magnetosphere, magnetosphere to ionosphere, ionosphere to atmosphere, and atmosphere to the geographic pattern of disruption. The Sun's 11-year activity cycle is the carrier wave. Longer cycles modulate its amplitude and determine how deep and sustained periods of reduced solar activity become. The approximately 208-year de Vries, or Seuss, cycle is the book's primary historical climate signal. When several consecutive 11-year minima become unusually deep, the result is a grand solar minimum lasting decades or nearly a century. The manuscript identifies 4 such minima in the past 6 centuries: the Wolf minimum from roughly 1280 to 1350, the Sporer from 1420 to 1570, the Maunder from 1645 to 1715, and the Dalton from 1790 to 1830. Each was associated with cooling and agricultural stress. Each occurred with the North Magnetic Pole in the Canadian Arctic. Each struck the same radius zones. The approximately 1,000-year eddy cycle modulates how deep de Vries troughs become. The medieval warm period occurred near an eddy maximum. The Little Ice Age unfolded as the cycle descended, providing a background in which the Maunder and Dalton minimums became severe. The approximately 2,500-year Hallstatt cycle modulates the eddy scale. The book places the present in a declining Hallstatt phase, with the eddy cycle beginning descent and the de Vries cycle approaching a trough. No one cycle is at its most extreme. The framework identifies their shared direction, combined with the pole's Russian Arctic position and a weakening magnetic field, as a convergence of planetary stress factors. This leads to the radius model. If electromagnetic organization is disrupted around the pole during solar minimum conditions, consequences should be strongest nearest the pole and grade outward with distance. Historical minimum period effects followed radius zones centered on the Canadian Arctic pole. But the pole has moved 2,200 kilometers. The radius has rotated. The model is dynamic, not permanent. Its geographic prediction depends on the pole's position during a specific minimum. History shows what happened under the old geometry. The physics of the current pole position determines where the book expects the next concentrated stress. In 1920, Serbian engineer Milutin Milanković worked in a Budapest library while interned during the First World War. His problem was immense: calculate how solar energy reaching every latitude changes across thousands of years as Earth's orbital geometry slowly varies. He combined three cycles: the shape of the orbit, the tilt of the axis, and the wobble of that axis, into curves of insolation across past and future time. He worked without computers. Decades later, ice cores showed that glacial cycles followed the orbital schedule he had calculated. The Epica Dome Sea project drilled 3,270 meters into Antarctic ice and recovered about 800,000 years of continuous climate history, 8 complete glacial interglacial cycles. The first orbital cycle is eccentricity, the changing shape of Earth's orbit. It operates principally near 100,000 and 413,000 years. Earth's current eccentricity is about 0.017, in the lower third of its range. Direct annual energy change is small, about 0.1%, but eccentricity amplifies or mutes precession by changing the difference between perihelion and aphelion. The second is obliquity, Earth's axial tilt. It varies from approximately 22.1 to 24.5 degrees over 41,000 years. The current tilt is about 23.4 degrees and decreasing. Greater tilt intensifies high-latitude seasons. Smaller tilt cools polar summers and favors survival of winter snow. The third is precession, the roughly 26,000-year wobble of Earth's axis. Polaris is not always the North Star. The axis once pointed toward Thuban and will point toward Vega again. Precession advances about 1 degree every 72 years and determines which season occurs closest to the Sun. Together these form the sky's long clock. They govern the distribution of solar energy across latitude and season, and they pace the advance and retreat of ice over hundreds of thousands of years. But the ice record revealed a problem Milanković's basic calculation could not completely solve. The 100,000-year problem is the central puzzle in Milanković cycle science. It has 3 parts. First is magnitude. Eccentricity causes the smallest change in total annual solar energy, about 0.1%, while obliquity and precession create larger changes in energy distribution by latitude and season. Yet for the past 800,000 years, ice ages have followed the weaker 100,000-year eccentricity rhythm. Second is timing. Deglaciations happen rapidly. The transition from maximum ice to minimum ice can occur in roughly 10,000 years, much faster than a gradual orbital change alone appears to imply. Something amplifies the orbital signal at termination boundaries. Third is asymmetry. Ice ages build slowly across tens of thousands of years, then end abruptly. The orbital forcing rises and falls more symmetrically than the climate response. The system enters glaciation slowly and exits quickly. Ice albedo feedbacks, carbon cycle changes, and ocean circulation are real mechanisms invoked to explain the pattern. The hidden axis proposes that geomagnetic behavior is an additional missing element. For magnitude, it proposes that eccentricity modulates cosmic ray variation, while geomagnetic strength controls how much of that variation reaches the atmosphere and affects clouds and chemistry. For timing, it proposes that geomagnetic excursions and intensity shifts can rapidly reorganize the atmosphere near termination boundaries. For asymmetry, it proposes a nonlinear feedback between field behavior and the loading or unloading of ice sheets. The manuscript labels these as framework inferences requiring systematic tests against paleomagnetic and paleoclimate records. It identifies the mid-Pleistocene transition, when glacial pacing shifted from approximately 41,000 to 100,000 years, as a possible threshold in the field's long-term evolution. Before that transition, the field configuration may have amplified obliquity. Afterward, it may have amplified the eccentricity precession interaction. The hypothesis is bold because it offers one connected explanation for magnitude, timing, and asymmetry. Its proposed physical bridge is the cosmic ray connection. Cosmic rays are high-energy particles, primarily protons and atomic nuclei, produced by supernovae, neutron stars, and other energetic processes across the galaxy. They arrive at Earth from every direction. The geomagnetic field deflects many of them, especially at low latitudes where the shielding is strongest. Near the poles, converging field lines allow more particles into the atmosphere. When cosmic rays penetrate the lower atmosphere, they ionize molecules. The resulting charged particles can participate in the formation of aerosols and condensation nuclei for water droplets. The Svensmark hypothesis proposes that changes in cosmic rays significantly influence low-level cloud formation and therefore surface temperature. The manuscript notes that the magnitude is debated while presenting ionization, aerosol formation, and cloud development as the physical pathway. The hidden axis connects this pathway to eccentricity. When Earth's orbit is more elliptical, the contrast between perihelion and aphelion becomes larger. The book proposes that this produces greater annual variation in solar wind shielding and, in turn, greater variation in galactic cosmic rays reaching Earth. Earth's magnetic field is the second gate. When it is strong, it deflects more cosmic rays despite variations in the solar wind. When it weakens, more penetrate to lower altitudes, and the orbital variation can exert a larger atmospheric effect. The proposed mechanism is therefore an interaction: eccentricity modulates cosmic ray variation, solar activity modulates entry into the inner solar system, geomagnetic strength modulates entry into Earth's atmosphere, ionization influences aerosols and clouds, clouds alter reflected sunlight. In the framework, the 100,000-year eccentricity cycle dominates when geomagnetic strength falls within a range that amplifies this cosmic ray signal. The 41,000-year obliquity rhythm dominates under another magnetic configuration. This chain requires empirical confirmation at every link. But the book identifies an event in the geological record that shows what can happen when Earth's magnetic shield is severely weakened. It happened 42,000 years ago. 42,000 years ago, during the Lost Champ excursion, Earth's magnetic field weakened to approximately 10% of its current strength. The poles wandered toward middle latitudes, and the magnetospheric shield was reduced to a fraction of its normal capacity. The excursion lasted several thousand years. At its peak, the book states that cosmic ray flux in the lower atmosphere approximately doubled. Carbon-14 and beryllium-10 production spiked, leaving synchronized signatures in ice, sediment, and tree rings. The manuscript presents three categories of consequence. In biology, Australian megafauna extinctions cluster in the Loschamp period, while European Neanderthals entered their final decline. It presents increased ultraviolet exposure, disrupted food webs, and changing plant distributions as possible added pressures. In the atmosphere, synchronized records show disruption in both hemispheres, including Australian aridity and changes in Southern Ocean wind and current patterns. Ozone disruption and increased ultraviolet radiation altered surface conditions and lower atmosphere chemistry. In culture, the expansion of European cave art at sites including Chauvet, Lascaux, and Altamira begins during the same broad period. The book recounts the proposal that shelter from increased ultraviolet radiation may have placed more people in caves, contributing to the conditions in which cave art flourished. The hidden axis does not predict a new Loschamp event in the coming decades. It states that the current field, about 15% below its 1840 measurement, is nowhere near Loschamp magnitude. Loschamp serves as an existence proof that severe geomagnetic weakening can accompany global atmospheric and biological consequences. The current picture is convergence without equivalence, relatively low eccentricity, decreasing obliquity, precession moving toward less northern summer energy, a weakening geomagnetic field, and de Vries, Eddy, and Hallstatt cycles all moving toward reduced solar activity. None is at its greatest extreme. The book argues that their simultaneous direction creates a compound stressor, not imminent glaciation, but geographically concentrated atmospheric stress operating against the powerful counterforce of modern greenhouse warming. Below that atmosphere, the geological system is already responding. On the night of November 9, 2021, a fissure opened on Iceland's Reykjanes Peninsula and lava reached the surface in a zone that had been quiet for roughly 800 years. There was no towering ash cloud. People walked close enough to feel the heat of new rock forming. Scientists placed instruments near the flow. Beneath the spectacle was the greater fact: the last eruptive period in this zone ended around 1240. Then came eruptions in 2021, 2022, 2023, and 2024. Grindavik was evacuated repeatedly as lava threatened roads, homes, and commercial structures. Iceland sits where the North American and Eurasian plates pull apart, above a mantle plume. The peninsula was never geologically dead. But the manuscript identifies accelerated crustal uplift, linked to loss of ice from Vatnajökull, as part of the changing pressure environment beneath the island. Ice is geology. 1 cubic meter weighs about 917 kilograms. A column 1 kilometer high exerts roughly 9 megapascals of pressure at its base, around 90 times atmospheric pressure. Greenland's ice reaches about 3,200 meters thick and depresses the bedrock beneath it by hundreds of meters. Remove ice and the land rises through isostatic rebound. In most regions, the mantle responds across thousands of years. Scandinavia and northern Canada are still rising from ice lost at the end of the last glacial period. Ancient shorelines in Scotland now stand above the sea. Iceland and West Antarctica respond much faster because the mantle beneath them is unusually hot and fluid. The manuscript cites uplift around 20 mm per year in active Icelandic zones and 40 to 50 mm per year in West Antarctica. Iceland makes the geological cascade visible. Atmospheric change redistributes ice. Ice loss unloads the crust. Rebound changes the pressure surrounding magma. The probability of eruptions rises. The ice moves. The crust responds. The magma stirs. The geological cascade has 4 links. Link 1, atmospheric reorganization changes precipitation. Storm tracks shift. Some regions receive more moisture, others receive less. Snow accumulation and melt change geographically. Link 2, redistributed ice changes the load on the crust. Land beneath lost ice rebounds. Land beneath growing ice subsides. Faults and magma chambers enter a new mechanical environment. Link 3, pressure changes affect volcanic and seismic systems. Reduced confining pressure allows dissolved gases to leave magma more easily, increasing buoyancy and mobility. Differential rebound changes stress along faults. Beneath marine ice, unloading affects submarine bedrock and volcanic systems. Link 4, eruptions return the cascade to the atmosphere. Sulfate aerosols injected into the stratosphere reflect incoming sunlight and temporarily cool the lower atmosphere. Geological activity amplifies the atmospheric disruption that initiated the chain. The result is a feedback loop: atmosphere to ice, ice to crust, crust to volcano, volcano back to atmosphere. Because geology responds with delay, volcanic amplification can continue after the solar driver begins recovering. West Antarctica is the southern analog to Iceland. Its ice sheet holds about 2.2 million cubic kilometers of ice and loses approximately 138 gigatons per year. Beneath it lies a 3,000-kilometer rift system and a province where the manuscript cites 138 buried volcanic structures. It predicts elevated volcanic probability as continued ice loss lowers confining pressure, without predicting a specific eruption or date. The Ring of Fire is the more distant expression. It contains roughly 75% of the world's active and dormant volcanoes and about 90% of its earthquakes. Tectonic forces remain primary. The framework adds a statistical prediction: mass redistributed from land ice to the global ocean subtly changes stresses in already strained subduction zones, elevating volcanic and seismic activity during minimum periods. The prediction is not a calendar of disasters. It is a testable increase in frequency across the system. History, the book argues, shows the geological cascade operating during grand solar minimums. The Maunder minimum began around 1645. As solar activity remained suppressed, the Little Ice Age intensified, the Thames froze, and alpine glaciers advanced. Major eruptions clustered through the following decades: Parker Peak in the Philippines, Hokkaido Komigatake in Japan, Sheveluk in Kamchatka, and repeated activity at Iceland's Grimsvatn beneath the Vatnajökull ice cap. The conventional reading treats eruptions as independent events that added cooling. The framework reverses the upstream causation: minimum period atmospheric reorganization, redistributed ice, changing ice loads altered crustal stress, volcanic probability rose, volcanic aerosols then amplified the cooling. The Dalton minimum provides the book's clearest example. It began near 1790. 25 years later, Tambora produced the largest eruption in recorded history. The following year, 1816, became the year without a summer and one of the most severe agricultural crises in recorded Europe and North America. The hidden axis reframes the sequence. Tambora did not independently create the entire crisis. It amplified minimum period atmospheric disruption already underway, while the preceding decades of altered climate and ice distribution formed part of the geological cascade that the framework proposes helped prime the eruption. Today, that cascade is presented as present tense. Iceland has entered repeated eruption after centuries of surface quiet. West Antarctic bedrock is rising rapidly beneath a thinning ice sheet and a major volcanic province. The Ring of Fire prediction will be tested as the solar minimum period develops. The framework does not name the date of a specific eruption. It predicts elevated geological activity during the minimum relative to surrounding solar maxima. The planetary mechanism is now in place: moving reference frames, a core-generated magnetic axis, solar electromagnetic coupling, nested solar clocks, orbital cycles, cosmic rays, ice redistribution, crustal rebound, and volcanic feedback. The ice moves. The crust responds. The magma stirs. The volcanoes wake. It has operated before. Episode 3 enters the historical proof. The oldest confirmed living bristlecone pine germinated while the pyramids were being built. It is not old enough to remember the last time the world changed. The Younger Dryas began approximately 12,900 years ago. We know it through the records the planet keeps, annual layers of snow compressed into Greenland ice, preserving isotopes, dust, chemistry, and bubbles of ancient air. At the Younger Dryas boundary, the handwriting changes. One layer records warmth. The next records cold. Within approximately 3 years, Greenland temperatures fell by something in the range of 10 degrees Celsius. This was change on a human scale. A person alive before and after the boundary could have watched an entire climate regime disappear. The GSP2, GRIP, NGRIP, and NEAM ice cores resolve both boundaries with exceptional clarity. The oxygen isotope record drops sharply at the onset, remains low for roughly 1200 years, then rises again near 11,700 years before present. The return to warmth took approximately 50 years. 3 years into cold. 50 years out. The framework reads that asymmetry as a clue. It proposes that the Gothenburg geomagnetic excursion rapidly disrupted the atmospheric organizing framework, while recovery of the field and the ocean circulation required decades. That first link is the framework's inference. The abrupt temperature shift itself is written directly into the ice. The Younger Dryas is where historical proof begins, not with a legend, but with annual layers in Greenland marking the moment one world ended. The Younger Dryas was not only a Greenland event. Its signature appears across every inhabited continent, though not everywhere in the same direction. In Europe, forests retreated and steppe and tundra returned. Britain and northern France took on conditions resembling northern Siberia. In North America, the Clovis culture disappears from the archaeological record near the onset, alongside the extinction of mammoths, mastodons, giant ground sloths, American horses, and other megafauna. The relative roles of climate and human hunting remain debated, but the timing is striking. In the Levant, the Natufian culture contracted. Communities that had begun cultivating wild cereals became more mobile as drought reduced the productivity of their landscape. In China, lake sediments and pollen indicate drought in the Yangtze Valley. Tropical South American glaciers expanded. Tropical Pacific sea surface temperatures cooled. The global pattern was not simple uniform cooling. It was reorganization. Its most important feature was the bipolar seesaw. While Greenland plunged toward near-glacial conditions, Antarctic ice shows southern warming. This opposite movement appears repeatedly in rapid climate events. The physical mechanism is the Atlantic Meridional Overturning Circulation, or AMOC. AMOC carries warm surface water north through the Atlantic, releases heat, and returns cold dense water southward at depth. When it weakens, the north loses that heat while heat no longer exported from the south accumulates there. North down. South up. One cause, two opposite effects. The seesaw and AMOC mechanism are established climate science. The framework's proposed addition is upstream, a geomagnetic disturbance initiating the atmospheric and meltwater changes that shut the circulation down. AMOC depends on density. Warm, salty surface water travels north, cools, becomes dense, and sinks. This overturning moves roughly 17 million cubic meters of water each second through the Atlantic, more than 100 Amazon rivers. Freshwater is its enemy. It dilutes the surface salinity, makes the water less dense, and can prevent sinking. Without sinking, overturning stalls and northern heat transport collapses. The broad scientific explanation for the Younger Dryas is a massive freshwater input to the North Atlantic. The argument concerns its source, timing, and route. Lake Agassiz, a proglacial lake larger than all the modern Great Lakes combined, has long been a leading candidate. But its best documented drainage events do not align cleanly with the onset, and their volume may not fully explain the modeled shutdown. Other proposed sources include Laurentide meltwater routed through the Mississippi, accelerated Atlantic iceberg calving, and European ice sheets. The framework proposes a distributed event, several meltwater sources, operating at once, driven by one atmospheric reorganization. It identifies the Gothenburg geomagnetic excursion as the possible trigger. The dating is not precise enough to prove causation. Estimates place the excursion broadly between 12,500 and 11,000 years before present, overlapping the Younger Dryas without fixing whether it led the onset by the required years or decades. The manuscript states this limitation directly. Its proposed test is geographic. Reconstruct the wandering pole's position, map where northern ice melt began, and compare the radius zones. A spatial match would support the mechanism. A mismatch would refute it. The data largely exists. The test has not yet been performed. For 1,200 years, the Younger Dryas was not an event. It was the world. A person born into its cold lived and died without knowing any other climate. 50 generations could pass beneath the same environmental regime. The survivors adapted through mobility, flexibility, and generalism. In Europe, dispersed cultures replaced patterns that had been possible in a warmer, more abundant landscape. In the Levant, the Natufian approach toward agriculture paused. In North America, hunters faced a continent losing much of its largest prey. Then, around 11,700 years before present, Greenland warmed by approximately 10 degrees Celsius within roughly 50 years. The framework proposes three systems converging in recovery. First, the Gothenburg excursion resolved and the atmospheric framework restabilized. Second, AMOC restarted, carrying ocean heat northward again. Third, precession had moved northern hemisphere summer toward perihelion, approaching maximum Holocene summer insolation. The convergence created a new configuration. Strong Atlantic heat transport and intense northern hemisphere summer sunlight strengthened the African monsoon. Rain reached the central Sahara. Lakes filled desert basins. Rivers crossed land now hyperarid. Vegetation amplified the initial forcing until 1/3 of Africa was green. The people best positioned for this transformation were descendants of those compressed by the Younger Dryas, mobile, adaptable populations who carried their survival toolkit into a generous new landscape. Over millennia, they built the astronomical tradition preserved at Nabta Playa. From the Younger Dryas came the Green Sahara. From the Green Sahara came the people whose descendants built the pyramids. The next proof is written where water once covered the desert. In 1933, explorer Laszlo Almasi entered a side canyon of the Gilf Kabir, deep in the Libyan desert. Inside a cave, he found painted human figures with arms extended, bodies horizontal, moving through water. People swimming, 500 kilometers from the nearest permanent water. The cave of swimmers confronts us with a world that existed and vanished. The African humid period lasted from approximately 14,800 to 5,500 years before present, 9,300 years, more than 4 times all recorded history. The transformation was continental. Desert became savanna. Lakes formed in empty basins. The evidence is preserved offshore, where Atlantic sediment cores record Saharan dust. During desert phases, exposed soil produces immense mineral dust flux. During the humid period, roots held the soil and that flux fell nearly to zero. A dark, organic-rich layer lies between the dusty eras before and after it. Within the Sahara, lake sediments preserve pollen from grasses, acacia, tropical trees, and moisture-dependent shrubs. Freshwater shells and fish bones remain in dry depressions. At Gabbero in Niger's Tenere Desert, cemeteries reveal thousands of years of lakeside occupation in a place now without water or shade. The scale is difficult to absorb. Roughly 10 million square kilometers, an area larger than the United States, changed ecosystem. The Sahara was not merely wetter. It became another world, and people inhabited that world long enough to regard it as permanent. The Green Sahara held many peoples across many millennia. Its earliest inhabitants followed game, harvested wild plants, and fished expanding lakes. Rock art records elephant, giraffe, hippopotamus, rhinoceros, buffalo, crocodile, and antelope with the confidence of artists depicting familiar neighbors. By approximately 7,000 years before present, cattle herding had become the dominant economic strategy across much of the region. Art shows herds, milking, leading, and cattle buried with their owners. These pastoral societies built circular stone structures, made pottery with intricate geometric decoration, and watched the sky. At Nabta Playa, 700 miles south of Giza, they constructed an astronomical complex between roughly 7,000 and 6,500 years before present. A stone calendar circle aligned with the summer solstice sunrise, the moment seasonal rains began. For pastoralists, this was not abstract mysticism. It was a survival instrument calibrated to the return of water. The broader arrangement has also been interpreted as encoding stellar positions, including Orion, through precessional drift. In the manuscript's account, Nabta Playa represents an astronomical tradition tracking changes too slow for one human life. Its significance is profound within the book's framework. The oldest confirmed astronomical observatory was not created by classical Greece or Pyramid-era Egypt. It was created by cattle-herding peoples in the Green Sahara. As the desert returned, their descendants moved toward the Nile, carrying their cattle culture, accumulated knowledge, and long observation of the sky. The astronomical tradition that culminated at Giza began beside a seasonal Saharan lake. The primary driver of the African humid period is well established. Precession moved northern hemisphere summer toward Earth's closest approach to the sun, producing approximately 7% more summer solar energy than today. The African monsoon is a heat engine. Land heats faster than ocean. Hot North African land creates low pressure, drawing moist Atlantic air northward. That air rises, cools, and releases rain. Stronger summer insolation strengthens the engine. Models estimate that orbital forcing raised monsoon rainfall roughly 17%. But pollen, lake, and vegetation evidence in some regions implies increases of 200 to 300%. The vegetation albedo feedback explains much of the amplification. Plants darken the surface, increase absorbed energy, deepen low pressure, bring more rain, and support still more plants. Yet the sediment record introduces a threshold problem. Both the beginning and end of the humid period occurred within decades to centuries, while precession changes over thousands of years. The system flipped rather than slid. A landmark study identified a threshold near 4.2% above present northern hemisphere summer insolation. Above it, humid savanna. Below it, desert. The vegetation feedback can sustain two stable states, but the framework proposes an additional push behind their rapid crossing. It attributes the onset amplifier to post-Younger Dryas geomagnetic recovery, and the termination amplifier to a declining field and approaching solar minimum. Orbital forcing remained the underlying driver. Vegetation maintained the states. Geomagnetic and solar perturbations, in the framework's model, pushed the system across the threshold. The connecting evidence appears inside the humid period itself. During the Younger Dryas, the African monsoon weakened even though orbital forcing was still building toward its northern hemisphere summer maximum. The Niger River outflow record shows less water and sediment reaching the Atlantic. Dust increased. The Green Sahara transformation paused while the north remained cold, then resumed when the Younger Dryas ended and AMOC restarted. In the manuscript's framework, that interruption demonstrates that orbital forcing alone did not control the monsoon. The oceanic and atmospheric configuration could override it. At the other end, the Green Sahara did not vanish in one clean step. As the system approached its threshold, wet and dry conditions flickered. For pastoral communities, each failed rainy season threatened cattle, grass, and human survival. The response was progressive migration toward persistent water. The Nile became the ultimate refuge. Its flow came from rainfall far to the south and east, beyond the dying Saharan basins. As people converged on the river valley, population density, competition, and the need for coordination increased. Dispersed pastoral societies became more hierarchical and politically complex. Their inheritance remained visible. Cattle became foundational in Egyptian sacred culture through Hathor, Apis, and the pharaoh's bovine power. The astronomical inheritance of Nabta Playa also entered the Nile Valley. This is why the book calls the African humid period its master proof. It demonstrates at continental scale that climate zones migrate. 10 million square kilometers changed from desert to savanna and back. People adapted, moved, carried their knowledge, and built something meant to last. In 1977, engineer Robert Bauval looked at Orion's belt and noticed that one star, Mintaka, sits slightly off the line made by Alnilam and Alnitak. He remembered that the smallest Giza pyramid, Menkaure, is similarly offset from Khafre and Khufu. He proposed that the pyramids form a map of Orion's belt. The debate that followed helped bring systematic archaeoastronomy into wider public view. The encoding mechanism is precession. Earth's roughly 26,000-year wobble changes where stars appear in the sky. Because precessional movement can be calculated, a stone alignment to a star can serve as a timestamp. Run the sky backward until the star meets the monument's axis, and the structure points to an astronomical moment. The framework therefore reads some monuments as coordinate markers in time. They need not date their own construction. They may refer to a moment remembered by their builders. The manuscript cites a 2017 statistical analysis of alignments stretching back tens of thousands of years as evidence that precessional knowledge may be far older than its formal attribution to Hipparchus. This interpretation is debated, and the book distinguishes confirmed alignments from proposed readings. At Göbekli Tepe, built beginning around 10,000 BCE, hunter-gatherers raised rings of T-shaped limestone pillars weighing up to 20 tons. The vulture stone has been analyzed as an astronomical record pointing to approximately 10,950 BCE, the Younger Dryas onset. The site was deliberately buried. Within the framework, that makes it an archive protected for a future civilization capable of reading the long clock. The Great Pyramid contains several layers of astronomical precision. Its sides align with the cardinal directions to within approximately 3.6 arc-minutes. Its narrow internal shafts are not ordinary ventilation ducts. The southern shaft of the King's Chamber aligns with Orion's belt near the construction era, while the northern shaft aligns with Thuban, the pole star of that time. These construction-era stellar alignments are the confirmed level of the evidence. The contested level is the ground plan. The Orion correlation proposes that the three pyramids mirror Orion's belt as it appeared around 10,500 BCE, with the Nile corresponding to the Milky Way. Quantitative criticism argues that the fit is approximate when the full geometry is modeled. The manuscript does not conceal that dispute. It calls the shaft alignments confirmed and the older ground plan timestamp contested. Angkor Wat provides another comparison. Its equinox and solstice relationships are documented. A broader proposed reading connects its temple plan with Draco around 10,500 BCE. That claim is likewise presented as unestablished. The geographic detail is striking. Giza is near 31 degrees east longitude, Angkor is near 103 degrees east. Their separation is 72 degrees. 72 years is the approximate time required for 1 degree of precessional movement. But deliberately establishing ancient longitude at that precision would require capabilities not known to have existed. The framework's honest position is that the correspondence is documented, its meaning undetermined, and the broader pattern testable. Across the book's monument record, several sites converge on a period near the end of the Younger Dryas and beginning of the present Planetary Age. Göbekli Tepe is proposed to encode approximately 10,950 BCE. The Giza ground plan and Angkor complex have each been proposed to point near 10,500 BCE. Nabta Playa preserves later astronomical alignments within the Green Sahara tradition. Other proposed examples include the Sphinx, Karnak, and Newgrange. Not every claim carries the same evidentiary weight. Some solar and stellar alignments are confirmed. Other precessional dates remain disputed. The framework's argument rests on the convergence across traditions. Cultures separated by continents and millennia repeatedly built their most durable monuments around long celestial cycles. The conventional explanation treats each site through its own religion, cosmology, or agricultural calendar. The framework offers a geophysical interpretation. It says the recurring reference period marks the planetary transformation at the Younger Dryas recovery and the beginning of the Green Sahara, the reference point from which this phase of the long clock is measured. In that reading, the monuments are not simply pointing at gods. They remember a moment when one world ended and another began. They preserve the astronomical position of that transition for civilizations able to calculate the sky backward. Whether every proposed timestamp survives future analysis remains an open question within the manuscript itself. But the confirmed astronomical sophistication is real, and the possibility of an archive in stone leads directly to history's next record, civilizations that collapsed while the clock continued to run. Around 1285 BCE, Ramesses II and Hittite king Muwatalli II fought the largest chariot battle in history at Kadesh. 15 years later, their states signed the earliest surviving peace treaty. Neither knew that both civilizations had roughly 70 years left in their existing form. By 1200 BCE, the Hittite Empire was gone. Hattusa was burned and abandoned. Egypt survived, but its power contracted, its territories were lost, and the new kingdom ended. The Bronze Age collapse was multi-causal: drought, earthquakes, migration, trade disruption, conflict, disease, and internal failure. The framework does not deny that complexity. It seeks an upstream cause for the convergence. The climate evidence begins with a megadrought. Sorek cave speleothems show sustained precipitation decline from around 1200 to 850 BCE. Anatolian tree rings identify an especially severe dry interval from 1198 to 1196 BCE, matching major destruction horizons. The Dead Sea fell more than 50 meters. Pollen records across Syria and Lebanon show forest and shrubland yielding to steppe. Archaeomagnetism adds the framework's geographic key. Fired clay and mud brick preserve past field direction and intensity. The record places the magnetic North Pole farther toward Eurasia during this era. Assyrian observations interpreted as aurora imply Mesopotamian cities were roughly 8 degrees farther poleward in magnetic latitude than today. Applied to the radius model, the eastern Mediterranean, Anatolia, and Mesopotamia lay deeper within that era's primary zone. The civilizations that collapsed occupied the stressed geography; those buffered by river irrigation were better able to persist. The Bronze Age collapse is not presented as an isolated case. The manuscript follows a repeating sequence through 4 civilizations. The Akkadian Empire collapsed around 2150 BCE during the 4.2 kiloyear aridification event. At Tel Leilan, fertile urban sediment gives way to centuries of sterile windblown material. Tens of thousands left, and the city remained empty. Between roughly 760 and 930 CE, the great lowland Maya cities were abandoned amid the most severe multi-year droughts in a 2,000-year regional proxy record. The same study connected the period to reduced solar activity. At the same time, Greenland ice recorded cold and dryness. Cold Greenland. Drought Yucatan. Simultaneously, the bilateral signature described by the framework. For the Western Roman Empire, a reconstructed weakening of the North Atlantic Oscillation corresponds with drought in the homelands of migrating peoples. Steppe carrying capacity declined. Huns moved west. Goths were pressed toward the Roman frontier. A climatic stress began a migration cascade that Roman institutions failed to absorb. Different places. Different cultures. The same 5-step pattern in the book's model: solar conditions change, atmospheric organization weakens within the relevant radius zone, persistent drought damages agriculture, populations move, receiving political systems destabilize. The geography changes because the magnetic pole changes. The physics, the manuscript argues, does not. History becomes the record of human decisions inside a planetary system that periodically reorganizes its zones of stress. For collapses span roughly 1800 years, Akkad, the Bronze Age powers, the classic Maya, and Western Rome. Their languages, economies, and institutions were different. The sequence was the same. Solar minimum conditions arrive or intensify. Atmospheric systems in the active radius zone weaken. Rainfall becomes unreliable. Agriculture does not fail everywhere in one year, it contracts persistently until reserves disappear and societies dependent on surplus begin to fracture. Migration begins in the drought zone and spreads instability into neighboring regions. In the manuscript's account, Mesopotamia occupied the active geography during Akkad. The eastern Mediterranean did during the Bronze Age collapse. The Maya lowlands showed an extended zone drought while Greenland showed primary zone cold. Central Asian drought helped set populations in motion during Rome's final century. The pattern does not mean every political failure has one cause. It means the environment sets pressures to which institutions respond well or badly. Some civilizations adapt. Some are buffered by rivers or distance. Others reach their limits. The conclusion of the historical proof is that climate zones migrate, monuments may preserve the long clock, and collapse follows a recurring physical sequence when vulnerable societies occupy the stressed geography. The manuscript then turns from history toward the present. If the radius zones have rotated, which places now lie beneath them? Which populations have no historical memory of primary zone conditions? And where will the pattern express itself next? Episode 4 maps the radius model. In the winter of 1709, Paris fell to -23 degrees Celsius. The Seine froze nearly half a meter deep. Saltwater harbors on France's Atlantic coast froze. Wine turned solid in cellar bottles. Trees split as water froze within their trunks. Livestock died in stalls, and the olive groves of Provence were killed to their roots. The harvest failed. Bread prices tripled. An estimated 600,000 people died in France from cold, famine, and the diseases that followed. This was the accumulated legacy of the Maunder minimum, the 4 decades of suppressed solar activity between 1645 and 1715. It was not one terrible winter. Repeated failures spread across Northern Europe, Scotland, Scandinavia, and the German states. At the time, the North Magnetic Pole sat approximately 2,200 kilometers southwest of its present position, in the Canadian Arctic. In the manuscript's model, its primary radius covered Greenland, Iceland, and the North Atlantic. Its outer primary zone covered the British Isles, Scandinavia, and Northern Europe. The radius zones produced 1709. Those zones have since moved 2,200 kilometers. The framework does not expect the next minimum to reproduce 1709 in the same geography. It expects an equivalent atmospheric stress to fall on regions with no cultural memory of primary zone conditions. Episode 4 maps that rotation, where the zones were, where the manuscript places them now, and how its predictions can be tested. The radius model defines each zone through historical consequences, not arbitrary lines. The inner primary zone is where agricultural civilizations ceased to exist during severe minimum conditions. Greenland's Norse settlements had endured for nearly 4 centuries. They maintained farms, churches, contact with Iceland and Norway, and a functioning European society. The final confirmed record is a marriage in 1408. When Europeans returned later, they found ruins. The Thule Inuit survived and expanded. Their Arctic technologies, hunting systems, and traditional knowledge gave them resilience that European agriculture lacked. Within the framework, the lesson is not that the people lacked character. Their social system was not adapted to the zone. The manuscript places the coming inner primary zone over the Taimyr Peninsula, the Laptev Sea coast, and the northernmost reaches of Siberia. These places are sparsely populated and not agricultural civilizations like Norse Greenland. But the historical warning remains: the inner zone is lethal to human systems that cannot adapt. This is the steepest part of the radius gradient. It does not mean one sudden catastrophe. It means progressive attrition as growing seasons, energy demand, infrastructure, and the economics of habitation move beyond the limits for which a society was built. The outer primary zone is where civilizations survived, but famine reshaped them. Scotland's 7 ill years of the 1690s brought repeated harvest failure. Grain did not ripen in cold summers. Early frost killed crops before harvest. Wet conditions caused them to rot. In some regions, 5 to 15% of the population died. Migration to the American colonies accelerated, changing the Atlantic world's cultural geography. In the manuscript's next minimum map, this zone includes northeastern China's grain provinces, the Russian Volga and Krasnodar grain belts, northern Kazakhstan, and Mongolia. These populations are vastly larger and more integrated into global food markets than 17th-century Scotland. The secondary zone is different. It produces serious disruption, elevated mortality, difficult harvests, and political stress, but institutions remain continuous. France in 1709 was devastated, yet it remained France. Its agricultural system recovered. The model places Northern Europe, Scandinavia, Iceland, and the British Isles in the next secondary or extended zone rather than their historical primary positions. Their risk does not disappear, but the manuscript describes this as a structural improvement. 3 bands, 1 gradient, inner primary attrition, outer primary famine, secondary disruption with institutional survival. The model now rotates those consequences from the old pole position toward the Russian Arctic sector. The manuscript calculates the rotation from the pole's displacement. It places the Maunder minimum pole near 80 degrees north, 95 degrees west, in the Canadian high Arctic. It places the current pole near 86 degrees north, 139 degrees east, in the Russian Arctic. Across Earth's surface, That movement is approximately 2,200 kilometers and roughly 95 degrees of longitude around the polar region. Because the zones are organized around the magnetic pole, they rotate with it, though their boundaries are not simple straight lines. Latitude and the elliptical geometry around a near-polar point change the exact result for each region. In practice, the manuscript moves Iceland from inner primary exposure towards secondary or extended exposure. Northern Scandinavia moves back from outer primary conditions. Northern China and Mongolia move forward into the outer primary zone. Northern Russia and Siberia move into inner or outer primary exposure depending on location. The qualitative picture is the central claim: the regions that carried minimum period stress during the 4th century instrumental record are stepping back, while a Russian Arctic-centered sector steps in. That claim creates a geographic test. If the severe effects remain concentrated in historical northern Europe and northeastern North America while northeastern China and Mongolia remain comparatively stable, the radius model fails. The rotation is meaningful only if consequences rotate with it. The framework calls its predictions science rather than prophecy because it states what would prove them wrong. Its primary prediction is that the next significant solar minimum will concentrate the strongest agricultural disruption, cold anomalies, and social stress in the rotated radius zones rather than the historical ones. Confirmation would include several consecutive years of below-average grain yields in northeastern China while northern Europe performs normally or better, East Asian polar vortex penetrations increasing while North American disruptions decline from their historical frequency, and Mongolian livestock mortality from ZUD events exceeding the 20th century baseline. Falsification would look like a 1709 equivalent Paris winter while Harbin remains within normal variation, repeated Scottish harvest failure while Heilongjiang grain remains stable, or historical zone geological activity returning while the new zones remain quiet despite the conditions the model identifies. The manuscript expects evidence to accumulate as the solar cycle descends through its projected minimum, with enough data by approximately 2035 for a meaningful interim judgment. The framework is offered to be tested, not believed. Its predictions are on the table. The geographic distribution of future effects will decide whether the radius is a working model or a failed hypothesis. Chapter 12 begins in the spring of 2030 with a hypothetical farmer, Wang Jianming, planting wheat in Heilongjiang province on the same black earth farmed by generations before him. He does not see a magnetic map or a solar cycle. He sees a late frost, soil running 2 weeks behind the old schedule, an autumn frost arriving early, and grain yields that no longer match the almanac his family trusted. The manuscript places this experience inside a solar timeline. Solar cycle 25 peaked in late 2024 and early 2025, stronger than cycle 24. It states that this complicated earlier grand minimum forecasts and required the expected timeline and depth to be recalibrated. It projects cycle 26 beginning around 2030 at below average strength, and cycle 27 around 2041 potentially weaker again. It also states plainly that current data cannot determine whether these cycles will constitute a true multi-decade grand minimum comparable to the Maunder period. The model does not require Maunder-level severity to be tested. It argues that a moderate extended minimum should still express effects in the new radius zones. Severity controls magnitude. Pole position controls geography. For Wang Jianming, that distinction becomes a calendar: how many frost-free days remain between planting and harvest. Heilongjiang, Jilin, and Liaoning hold approximately 100 million people and form one of China's critical grain regions. Their rice, corn, soybeans, and wheat depend on a growing season of roughly 150 days. The margin is thin. A last frost 2 weeks late postpones planting. A first frost 2 weeks early ends harvest before grain matures. Both in 1 year can cause severe loss. Repeated together across several years, they challenged the entire agricultural system. The book emphasizes the adaptation gap. The region's varieties, planting dates, storage systems, and financial assumptions were built for the climate of the last century. Knowledge of 130-day crops, handling wet early harvests, and surviving repeated failures is not deeply embedded because primary zone conditions are outside living tradition. Humans will adapt, the manuscript says. But variety development, distribution, changed practice, and institutional learning take time. The dangerous period is the transition after the old climate regime stops matching expectations and before the new toolkit has reached the farm. The framework predicts northeastern China would enter that transition during the minimum's peak years. The risk is not a lack of ingenuity. It is the speed at which a system serving 100 million people must change. On the Mongolian steppe, approximately 1 million people depend on nomadic or semi-nomadic pastoralism. In good years, rainfall supports large herds. In Adzud, deep snow, ice, or extreme winter conditions prevent livestock from reaching food. The Adzud of 2009 and 2010 killed approximately 9 million animals, about 1/4 of Mongolia's livestock. Tens of thousands of families lost food and income, and international assistance was required. The manuscript treats that event as secondary zone variability, then predicts that outer primary conditions could produce severe events more frequently, perhaps several in a decade rather than once in a generation. Farther north, Siberia presents a different vulnerability. Cities, railways, roads, pipelines, and buildings were engineered for extreme but historically predictable cold. The framework does not simply predict colder averages. It emphasizes volatility, rapid changes and repeated freeze-thaw cycles. For infrastructure built on permafrost, thaw and refreezing can destabilize foundations. Ground subsides. Roads crack. Buildings tilt. Pipelines shift. These stresses compound damage already projected under warming scenarios. The Mongolian herder and Siberian infrastructure worker face different systems, but the same transition problem: institutions designed around 20th century variability encountering conditions the model places outside that design history. What does a primary zone feel like? The manuscript returns to historical testimony. Iceland lost approximately 1/4 of its population during the late 17th century through accumulated crop failure, livestock death, and disease. Reserves could cover one bad year, but not 3 consecutive failures. Greenland's Norse settlements ended. Scotland's 7 ill years left grain unripe beneath early snow, families without food, and a rural social order close to breaking. The book does not claim the next minimum will equal Maunder severity. It uses these cases as the qualitative boundary of primary zone risk, not inconvenience, but the point where climate becomes incompatible with systems that were never designed for it. The Southern Hemisphere has a parallel. The manuscript describes Southern Australia's cool season rainfall decline and Northern Australia's strengthening monsoon as an already measurable bilateral split. It predicts those trends will deepen during the minimum. For Western Australian wheat growers, less winter rainfall threatens the present grain belt. In the Northern Territory, greater monsoon rainfall increases flood and infrastructure pressure while potentially improving dry season livestock carrying capacity. New Zealand remains buffered by ocean but faces greater southern variability. The radius is a gradient in both hemispheres. Its consequences depend on what each society has built, planted, and learned under the climate it assumed would continue. The preparation window turns geography into action. For northeastern China, the manuscript calls for cold-resistant, short-season crop varieties, storage capable of handling early wet harvests, and agricultural guidance for altered planting and harvest dates. For Mongolia, it calls for emergency feed reserves positioned before winter, veterinary capacity prepared for stressed herds, alternative income for pastoral households, and a proactive rather than reactive international response. For Siberia, it calls for wider permafrost monitoring, conservative construction standards, and contingency planning for pipelines and power systems before extreme events. For southern Australia, it identifies water capture and storage, faster adoption of drought-adapted varieties, and investment in northern production capable of replacing some southern losses. These are not exotic technologies. They are the familiar work of agricultural adaptation, winterization, engineering margins, and reserves. But timing determines their value. Preparation before disruption is prevention. Preparation after disruption is emergency response. The framework says planetary physics provides the warning, but cannot make the human decision. Whether the next minimum becomes managed disruption or unmanaged catastrophe depends on what institutions do while the window remains open. Chapter 13 begins with the ordinary appearance of disaster. When the Akkadian system entered decline, a low river and a short barley crop may have looked like familiar drought. What its administrators could not see was that rainfall was changing across the entire radius geography, from the Mediterranean toward the Industry. Every affected civilization needed grain in the same years. There was no outside surplus waiting nearby. Modern disaster planning assumes geographic containment. If one region fails, another exports food, credit, fuel, and assistance. The global food system depends on disruptions being partly independent. The radius model violates that assumption. Regions within the same zone do not experience identical weather, but they face directionally correlated pressure at the same time, shorter growing seasons, disrupted rainfall, and lower yields across multiple producers. This is why the manuscript's disaster map matters. It is not a calendar of exact events. It is a structural risk map showing where simultaneous stress could defeat diversification strategies built on the old geography. The book assigns 4 agricultural tiers: abandonment risk in the inner primary zone, sustained famine risk in the outer primary zone, institutional resilience tests in the secondary zone, and biological cascade risk across the extended zone. Tier 1 covers the northernmost Russian agricultural margins within approximately 1,500 kilometers of the pole. The risk is progressive abandonment as growing seasons and operating costs make sustained settlement uneconomic. Tier 2 extends roughly 1,500 to 4,000 kilometers and contains the most consequential food risks. Northeast China produces a major share of China's grain. The Volga and Krasnodar belts support Russia's position as a leading wheat exporter. Stress there transmits through markets to countries dependent on Russian supply. Kazakhstan, Mongolia, and Kyrgyzstan form a steppe corridor whose pastoral economies are sensitive to drought and cold and whose safety nets may struggle with multi-year pressure. Tier 3, approximately 4,000 to 6,000 kilometers from the pole, includes Northern Europe and the East Asian coastal economies. Northern Europe retains adaptations built through centuries of harsher exposure. Japan, Korea, and coastal northeastern China face infrastructure stress from unusually frequent cold incursions. Tier 4 extends into the Horn of Africa, Arabian Peninsula, South Asia, and Sahel. Here the framework predicts biological cascades rather than direct cold, alternating drought and rainfall creating locust breeding opportunities, disease vectors, and crop pathogens in already stressed food systems. Different tiers. Different failure modes. One correlated geography. Infrastructure fails when conditions exceed its design envelope. That envelope comes from the historical record plus a safety margin. The radius rotation creates a mismatch. Energy, water, transportation, and buildings in the new zones were designed during secondary or extended zone climate history. The book uses the 2021 Texas freeze as a small-scale illustration, infrastructure built for subtropical conditions failed when extreme cold arrived. In the new zones, the exposure spans cities of millions and continental resource networks. Heating demand can exceed generating capacity while gas equipment freezes. Wind turbines ice. Solar panels collect snow. Hydroelectric systems face ice and altered flow, while backup generation experiences the same stress. Water systems face burst pipes during cold events and longer-term disruption when snowmelt, monsoon, and groundwater recharge stop matching their design assumptions. The response is technically understood: winterize gas infrastructure, increase reserve margins, build cold-rated backup capacity, distribute energy storage, protect pipes, and design water systems for greater variability. The difficulty is scale and time. Infrastructure can be strengthened gradually before a crisis or rebuilt rapidly after failure. The physical work may be similar. The human and economic cost is not. Climate stress does not automatically cause political collapse. The manuscript states that outcomes depend on institutions, leadership, support, and the exact form of pressure. It does not assign exact collapse dates. It identifies structural vulnerability. Mongolia receives the highest acute risk designation because so much of its economy and identity depend on pastoralism, while its fiscal capacity may not absorb repeated ZUD-scale emergencies. The Central Asian steppe is identified as a migration origin corridor. Historically, reduced carrying capacity moved populations toward surrounding civilizations. Modern states are not ancient nomadic confederacies, but food and income loss can still drive people north into Russia, east into China, and west toward Europe while those receiving systems manage their own stress. The key preparation gap is timing. Cold-tolerant crops may require 5 to 7 years from research to widespread adoption. Grain reserves are cheaper to build during ordinary harvests than during panic. Winterizing equipment costs less than replacing destroyed networks. Every year before disruption improves the ratio of prevention cost to response cost. Every delayed year narrows the options. The radius has rotated. The manuscript says risk models calibrated to the old pole position carry uncharted exposure. Institutions that read the new map can choose managed disruption. Those that do not may discover the map through failure. Episode 5 translates the framework into strategy and markets. In the summer of 2010, Western Russia endured an extraordinary heat wave. Moscow exceeded 38 degrees Celsius. Peat and forest fires burned, and wheat across the Volga basin and southern Russia was scorched before harvest. In August, Russia banned wheat exports. Global prices surged. Countries dependent on Russian grain, including Egypt, Turkey, Bangladesh, and many others, scrambled for supply. The World Bank estimated that the resulting food price spike pushed another 44 million people below the poverty line. 2 years later, governments fell across the Middle East and North Africa. Food inflation was not the only cause of the Arab Spring, but research has identified the Russian export ban as one contributing pressure. A drought in Russia. An export ban. A price shock. Political upheaval on another continent. The manuscript does not claim to predict individual weather events like the 2010 heat wave. It makes a structural claim: the Volga and Krasnodar grain regions now lie within the next minimum's outer primary radius. It predicts not one failed summer, but repeated growing season disruption. If a single Russian wheat ban contributed to political change abroad, what would a decade of structural grain stress do? That, the book says, is what markets do not know. Markets price risk with historical data and forward models. Both usually assume that the future's geography of risk will resemble the past. Places historically unstable remain risky, while places historically dependable remain stable. The radius zone rotation breaks that assumption. The magnetic pole's 2200 km displacement has moved the book's minimum period risk geography by roughly 95 degrees of longitude. Actuarial tables were built from a Canadian Arctic pole era. The manuscript argues that Russia, Mongolia, Kazakhstan, and northeastern China are entering an exposure absent from those tables. The mispricing persists because conventional models do not include magnetic pole position as a variable. They cannot estimate primary zone loss frequency in places that have never occupied that zone during the instrumental record. The first significant minimum in the new geography would therefore create correlated actuarial surprises across agriculture, insurance, commodities, infrastructure, and sovereign risk. Historical stability would become a misleading baseline. This is the chapter's central market thesis. The models are not necessarily calculating badly. They are calculating from a map the framework says has moved. The surprise would not be one extraordinary loss. It would be many losses occurring together because the regions share the same radius exposure. Russia exported approximately 45 million metric tons of wheat in the 2022 to 2023 crop year, close to 1/5 of global wheat trade in the manuscript's account. Much of it comes from Krasnodar and the Volga Basin. Their historical yield averages were established while these regions occupied secondary or extended minimum zones. The book predicts that outer primary variability will lower realized yields through repeated late frosts, early autumn cold, and unreliable seasons. It proposes a possible 15 to 25% sustained reduction during the minimum period if the historical outer zone analogy holds at modern scale. Combined with stress in northeastern Chinese grain, that would become a supply shock unlike the isolated failures modern markets are designed to absorb. Normally, drought in one exporter can be offset elsewhere. The radius model predicts correlation: Russia, northeastern China, Kazakhstan, and Mongolia under pressure in the same years. Secondary regions may also face their own disruptions. Futures curves, options, and supply chain insurance are calibrated to largely asynchronous failures. The manuscript argues they underestimate a multi-region event generated by one geographic system. The risk is not merely that one country harvests less. It is that every usual substitute becomes more expensive at once. Rotation also creates relative beneficiaries. The manuscript identifies Western Canada as the most important agricultural opportunity. Alberta, Saskatchewan, and Manitoba developed cold-resistant crops, storage capacity, and difficult season knowledge under centuries of Canadian Arctic exposure. As the zone shifts eastward, those adaptations remain while the atmospheric burden retreats. Scandinavia and Northern Europe present a smaller version of the same pattern, existing cold climate systems operating under what the framework expects to be less severe minimum exposure. For long-horizon commodity positioning, the book therefore proposes a geographic rebalance away from new primary agricultural regions and toward Western Canada, Scandinavia, New Zealand, and Northern Australia. It presents this as strategic positioning, not a short-term trade. The framework explicitly does not guarantee profit at a specific time. Markets can remain mispriced, and the timing of repricing cannot be known precisely. The thesis is a physical overlay for investors whose decisions extend through 2035 and 2040, structural headwinds in the new primary zones, structural tailwinds in the stability zones, and a scarcity premium when dependable production becomes harder to find. Energy responds to cold within hours rather than growing seasons. The new primary and secondary zones include regions whose systems were built from historical demand. During an extreme cold event, heating use spikes as equipment not designed for the conditions can fail. The manuscript identifies liquefied natural gas as the most immediate commodity implication. Japan, South Korea, and northeastern China are major LNG importers. Severe East Asian cold raises spot demand beyond contracted baselines. More frequent events mean repeated demand surges and greater value for import terminals, storage, and flexible supply. Australian, Qatari, and Pacific Access North American exporters are identified as potential beneficiaries of this structural demand uplift. Insurance faces the inverse problem. Coverage in Kazakhstan, Mongolia, and northeastern China is expanding just as the framework says loss frequency may rise. Historical actuarial experience contains no new primary minimum events for those regions. Reinsurers could therefore accumulate correlated agricultural exposure while believing it is geographically diversified. For sovereign risk, the same physical stress appears as fiscal burden, food support, infrastructure repair, emergency response, and lower production. The manuscript proposes treating radius exposure as a long-horizon factor in countries whose credit ratings were built from the old geography. Chapter 15 returns to the year 376. At the Danube, Roman commander Lupicinus received hundreds of thousands of Gothic refugees fleeing the Huns. Roman officials admitted them, then stripped them of food, weapons, and assets through corruption and incompetence. Hunger and betrayal became revolt. 2 years later, Rome suffered catastrophe at Adrianople and Emperor Valens was killed. The crossing was the final visible link in a cascade that began far away. Drought reduced the Central Asian steppes' carrying capacity. Huns moved west. Goths fled. A frontier designed for manageable movement received a mass displacement it could not process. Roman intelligence was sophisticated for its age, but it lacked a framework connecting Central Asian climate, Hunnic economic stress, migration, Gothic displacement, and pressure at the Danube. Modern militaries possess satellites, signals intelligence, economic monitoring, open-source analysis, and worldwide networks. The manuscript argues that data is not the missing resource. The missing resource is a geographic model telling planners which signals to prioritize, where to watch, and how an environmental cascade becomes a security mission. The strategic edge is foreknowledge. Current military climate doctrine recognizes climate as a threat multiplier. The manuscript describes that as genuine progress, but says the approach remains retrospective. It studies where environmental stress previously correlated with conflict and projects those places forward. The radius rotation would make that map incomplete. Historical primary zones are stepping back. Northeastern China, Mongolia, Central Asia, and northern Russia are stepping into the new exposure without a comparable instrumental history. The framework offers 5 forms of operational advantage. First is intelligence collection repositioning, establish baselines in the new zones before instability raises the noise. Second is alliance development. Relationships with receiving zone countries are stronger when built before migration or resource pressure begins. Shared intelligence, border protocols, humanitarian access, and institutional trust require years. Third is humanitarian logistics. The manuscript identifies routes from Mongolia toward Russia and China, from Central Asia through the Kazakh and Caspian corridors, and from northeastern Chinese agricultural regions toward eastern megacities. Prepositioned food, water, medical systems, transport, and airlift can turn unmanaged displacement into an organized response. Preparation does not militarize a humanitarian crisis. It gives institutions the capacity to keep one from becoming a security collapse. The most sensitive strategic claim concerns nuclear-armed states. Russia and China occupy primary or outer primary territory in the model and may face agricultural, infrastructure, and internal migration stress during the 2030s. The manuscript does not predict that either country will start a war because of climate stress. It states that the relationship between domestic pressure and external conflict is not mechanical. Leadership, institutions, political constraints, and foreign response remain decisive. Its narrower prediction is that both states may confront internal stress not incorporated into plans built from historical climate data. Governments under such strain may become more reactive, more vulnerable to miscalculation, or more inclined toward demonstrations of strength. Knowing that trajectory in advance can support deterrence and de-escalation. Signals can be calibrated to avoid unnecessary provocation. Intentions can be communicated clearly during what the book identifies as a higher risk window from approximately 2033 to 2038. At the grand strategy level, the distinction is anticipation versus reaction, aligning diplomacy, information, military posture, and economics before events force action. The framework does not decide what governments will do. It proposes where pressure may concentrate so planners can reduce the chance that stress becomes conflict. Rome had the tools to manage the Gothic arrival. It could have organized food, land, integration, and orderly settlement. It had soldiers, administration, and centuries of frontier diplomacy. What it lacked was the understanding that the crossing was not an isolated border problem. It was the leading edge of a cascade whose source lay thousands of kilometers away. Without that map, Roman actions remained tactical: manage today's crossing, fight today's battle, negotiate today's agreement. Each response could appear rational while the larger system continued delivering pressure. The manuscript says the modern cascade begins with contracting growing seasons and stressed pastoral land. It proceeds through economic loss, internal migration, political instability, cross-border pressure, and regional conflict risk. At each stage, an intervention can interrupt the sequence. Rome in 350 would have had 28 years before Adrianople. The book estimates that modern planners have 8 to 13 years from its 2025 starting point to the projected 2033 to 2038 peak, enough to establish intelligence baselines, partnerships, logistics, and doctrine. The greatest advantage is not simply superior weapons. It is knowing where and when the next crisis may concentrate before the crisis makes that knowledge obvious to everyone. Chapter 16 opens with the Homestead Act and the American Great Plains. Settlers broke deep prairie sod and planted productive soil. By the 1890s, the plains had transformed world grain markets. Then came the drought of the 1930s. Without the native roots that once anchored it, topsoil rose into immense storms. Black Sunday carried a dust wall estimated at 1,500 meters high. Millions left. The settlers were not foolish. They were given a true picture of the land during its wet phase, but not the longer record showing regular and severe drought. The book uses the Dust Bowl as a warning against building from a short historical window. It proposes a three-pillar stability assessment. Pillar 1 is electromagnetic atmospheric stability, distance from both historical and new primary zones. Pillar 2 is agricultural climate trajectory, a stable or improving growing environment over 20 to 50 years, including temperature, rainfall, and season length. Pillar 3 is water security, reliable rivers, rainfall, or aquifers sufficient for the intended land use. Only where all three converge does the manuscript call the ground genuinely stable. Western Canada is the framework's strongest Tier 1 stability zone. First, the magnetic pole has moved away from the Canadian sector. Second, the agricultural climate zone is projected in the cited study to expand northward across Alberta by approximately 932 kilometers by 2099. Third, the region combines Rocky Mountain meltwater, perennial rivers, and prairie aquifers, though each has limitations. The Peace River country already produces canola, spring wheat, and barley near today's northern crop margin. The manuscript sees shorter season soybeans becoming increasingly viable, grain corn later in warmer microclimates, and specialty grains and pulses over a longer horizon. Its favored investment period is 2025 to 2065, when growing seasons expand, glacier meltwater remains near its peak contribution, and global markets may value reliable grain most highly. Priorities include grain elevators, roads and rail to Pacific ports, water capture, and renewable power for processing and cold storage. The opportunity is not simply more land. It is the infrastructure that converts a northward-moving agricultural margin into dependable export capacity. The Nordic arc offers a different stability case. Norway, Sweden, Finland, Denmark, and Iceland are moving away from their historical primary zone exposure. Their agricultural frontier is smaller, so the opportunity lies in greater productivity and crop diversity rather than vast new acreage. The manuscript points to soybeans becoming experimentally viable in southern Sweden and grain corn approaching viability in Denmark. It also highlights a non-agricultural advantage: cool climates, abundant hydroelectric and nuclear power, political stability, and reliable infrastructure make the region attractive for data centers and other long-duration digital assets. New Zealand is the southern anchor. Its position nearer the shifting South Pole creates some secondary zone variability, especially in the South Island, but the Southern Ocean buffers the extremes of continental interiors. The North Island receives the more favorable assessment. The Canterbury Plains retain moisture advantages from the Southern Alps. Food self-sufficiency, renewable energy, political stability, and geographic isolation from major migration corridors reinforce the case. These regions are not called risk-free. They are places where the book's three stability pillars overlap more strongly than elsewhere. Building in a stability zone is not enough if crops and infrastructure still reflect the old climate. For the Peace River corridor, the manuscript proposes a sequence: shorter season soybeans from 2025 to 2035, grain corn in suitable microclimates from 2035 to 2045, then pulses and specialty grains into 2060. Water capture and on-farm storage are the enabling investments. Northern Australia presents the inverse of the drying south. The book predicts more monsoon rainfall across the Kimberley, Top End, and Gulf country, with infrastructure, not water, as the constraint. The Ord River irrigation area provides its example: irrigated production of sugarcane, tropical fruit, chickpeas, and other crops. The framework imagines a broader northern system growing sorghum, tropical corn, cotton, sugar, mangoes, and melons, with processing and storage supporting year-round exports to Asia. The claim is strategic rotation: shift productive capacity toward places where water, atmospheric stability, and agricultural trajectory supported, while adapting each region's crop portfolio to the conditions expected there. Stable ground becomes useful only when the right systems are built upon it. The preparation window and the investment window are the same period viewed from different sides. An elevator built in Western Canada before 2030 could be operating during the book's projected 2033 to 2040 stress period. A Norwegian data center built beforehand could serve clients facing instability elsewhere. Water capture completed in Northern Australia could support production while southern rainfall declines. The same conditions that create stress in the new primary zones create scarcity value for stable production. Building early is therefore both resilience and positioning. The framework does not promise a specific return, a particular market date, or a predetermined geopolitical outcome. It says the map can guide long-duration choices: where to monitor, where to harden, where to build alliances, and where physical assets may endure. 9,000 years ago, the Green Sahara peoples moved toward remaining water as their world changed. Their descendants carried knowledge into the Nile Valley and built structures that lasted. The lesson, as the manuscript gives it, is not only that worlds change. Those who read the signs early can move toward stable ground before urgency removes their choices. The stable ground is mapped. Episode 6 puts the complete framework on trial. Chapter 17 opens in Egypt's eastern delta, around the end of the Bronze Age. The Apura Papyrus describes the end of a world, a river transformed, empty fields and granaries, unburied bodies, foreigners moving through the land, and a social order turned upside down. The manuscript presents it as an independent Egyptian account of environmental catastrophe and civilizational reversal from roughly the same broad era associated with the Exodus narrative, while acknowledging that the historical relationship of Exodus to specific events remains debated. The chapter's purpose is not to settle that debate. It is to examine the plague sequence as a cascade. Its proposed upstream cause is atmospheric reorganization in the eastern Mediterranean radius zone during a Bronze Age solar minimum. Under that reading, the Nile's weakened catchment and reduced flow begin a chain of ecological consequences. The manuscript's central argument is that the plagues form a mechanistic sequence rather than 10 disconnected events. Water disruption leads to ecosystem failure. Ecosystem failure drives insects, livestock disease, human illness, crop destruction, food contamination, and political breakdown. Whatever judgment the evidence ultimately supports, the sequence matters because the book treats it not only as a reading of the past, but as a template for recognizing a cascade before it reaches its terminal phases. The manuscript begins the proposed cascade with water. Severe drought in the Nile catchment reduces the river's flow and raises its temperature. In stagnant, warming water, the book proposes that a burgundy blood algae bloom could stain the river red and produce toxins that kill fish. Fish die. Frogs leave the water. Decomposing biomass creates a resource pulse for insect populations. Biting insects become disease vectors among livestock already weakened by poor forage. When draft animals die, the next planting season is damaged before the current famine has run its course. The same compound pressures then reach people: compromised water, decomposing animal matter, elevated vector populations, and malnutrition. The boils and infections of the plague account become, in this reading, the health effects of a failing agricultural and ecological system. The terminal plague is interpreted through stored grain. After water failure, livestock loss, hail, and locust destruction, grain becomes the last food buffer. The manuscript proposes that warm, humid storage conditions allowed molds and mycotoxins to develop. In a social system where firstborn sons received priority access to food, preferential consumption could also mean preferential exposure. This is the book's proposed mechanism, not a direct measurement of an ancient event. Its significance lies in the structure: each stage creates the conditions for the next. The atmospheric origin of the cascade returns in hail, locusts, and darkness. The manuscript connects severe hail to convective instability within a reorganized Mediterranean circulation. It then points to the biological precision of the locust sequence. Desert locusts respond to an alternation: drought concentrates surviving populations, then rainfall produces vegetation and explosive reproduction. The 2019 to 2020 East African crisis is presented as a modern proof of concept. Cyclones delivered exceptional rain to the Arabian Peninsula. Several breeding generations followed, and swarms moved into East Africa, threatening the food security of millions. The book links that alternation to Indian Ocean dipole variability, which its framework predicts will intensify during the coming minimum. For 3 days of darkness, the manuscript offers two possible mechanisms: extreme dust driven by altered wind patterns, and volcanic ash associated with the geological stress cascade. It notes that the chronological relationship between the Santorini eruption and the Bronze Age collapse remains debated. This qualification matters. The chapter is assembling a proposed explanation, not erasing uncertainty. Its argument is that water, insects, livestock, human health, hail, locusts, dust, geology, and food storage can form one escalating system. A society experiences separate disasters. The framework asks whether those disasters are links in a single chain. The chapter then turns the cascade forward. In the Horn of Africa and Arabian Peninsula, the manuscript predicts stronger Indian Ocean dipole variability and shorter recovery periods between locust breeding triggers. It does not claim that the region will reproduce all 10 plagues. It predicts that the underlying sequence, atmospheric disruption, water stress, ecological amplification, agricultural loss, and disease pressure, will remain recognizable. In South Asia, the book applies the same logic to the Indus and Ganges systems. Monsoon disruption reduces river flow. Water quality declines. Biological stress increases. Locust breeding zones along the India-Pakistan frontier create the potential for interacting outbreaks. But this is also where the book changes direction from warning to intervention. River temperature, level, and algal blooms are phase 1 signals. Insect vector density is a later signal. Locust breeding conditions are later still. The manuscript argues that existing water, public health, livestock, and FAO monitoring networks already observe much of this information. What is missing, in its view, is a common cascade model telling those systems which signals belong together and what may follow. Intervention becomes more costly with each phase, water management first, then livestock movement and vaccination, then aerial locust control and emergency food reserves. The cascade can be interrupted. The chapter closes with a simple claim: there is still time. Chapter 18 begins in the British Museum in 1872. George Smith was translating clay tablets excavated from Nineveh, once part of the library of the Assyrian king Ashurbanipal. When Nineveh was destroyed, the fire baked the clay and preserved an archive that remained buried for roughly 24 centuries. On one fragment, Smith recognized a great flood, a worn survivor, a boat, animals, a mountain, and birds released to search for land. The tablet belonged to the Mesopotamian flood tradition preserved in the Epic of Gilgamesh. It was older than surviving biblical manuscripts, and its structure closely paralleled the story of Noah. The book widens the question. Flood and world destruction narratives appear in Mesopotamian, biblical, Hindu, Mesoamerican, Norse, Aboriginal Australian, and other traditions. Some may reflect contact or literary dependence. Others arose across cultures without documented contact during the relevant periods. What experience were they preserving? The manuscript proposes that these traditions are separate transmissions of a shared memory, the Younger Dryas catastrophe. It argues that cultural memory traveled through stories, while an astronomical coordinate traveled through monuments. This is a framework inference. The existence of the tablets and the widespread narratives is evidence. Their proposed common origin is the book's synthesis, a claim offered for testing, not a settled conclusion. The synthesis depends on the depth of ancient astronomical knowledge. The conventional account credits Hipparchus, around 150 BCE, with discovering the precession of the equinoxes, the approximately 26,000-year wobble that changes stellar positions over millennia. The manuscript points to research arguing for much earlier knowledge. It cites a 2017 statistical analysis by Martin Sweatman and Alastair Coombs comparing carved animal symbols and monument orientations with reconstructed ancient skies. That study reported correspondences extending as far back as the Lion Man carving, around 38,000 BCE. The book interprets this as evidence that a precessional astronomical tradition reached deep into the Paleolithic and survived later disruptions. That conclusion remains part of the framework's contested synthesis. But if sustained by further work, it changes how the monuments are read. Their alignments become more than local seasonal markers. They become coordinates in the sky's long clock. The manuscript follows a chain: knowledge accumulated across generations, survived the Younger Dryas, passed through Green Sahara populations, and entered the monumental cultures of the Nile and beyond. A single observer could not watch a full precessional cycle. The knowledge therefore required transmission, measurement handed from one generation to the next across spans longer than any individual life and, eventually, longer than the institutions that first preserved it. The book follows 6 traditions. Mesopotamia preserves the flood story and precise planetary records, along with the cosmological number 432,000, which the framework reads as related to the precessional constant. Egypt preserves Zep Tepi, the first time. The manuscript connects Giza's proposed precessional reference near 10,500 BCE with the post-Younger Dryas reorganization and the Green Sahara's beginning. Hindu cosmology organizes time into vast yuga cycles and carries another multiple of 432,000. The book raises, without resolving, whether this numerical convergence reflects shared astronomical inheritance. Aboriginal Australian traditions preserve detailed astronomical knowledge and memories of coastlines flooded roughly 12,000 years ago, including accounts associated with the separation of Tasmania from mainland Australia. Plato's Atlantis narrative places a destroyed prior world near the end of the Younger Dryas. The manuscript does not claim a literal sunken island civilization. It asks whether the story preserves transformed memory of a planetary transition. Mesoamerican traditions describe previous world ages destroyed before the present one and preserve sophisticated astronomical cycles. Across these traditions, the book identifies 2 recurring elements: a prior world ended, and time moves through large, intelligible cycles. Its inference is that myth and monument became 2 durable channels carrying one long warning. Why build in stone? The manuscript accepts that monuments served religious, political, funerary, and calendrical purposes. It adds another proposed function. The astronomical tradition, it argues, understood that climates and worlds change on timescales longer than civilizational memory. Institutions fail. Libraries burn. Languages drift. Oral accounts transform. Stone remains, and the sky provides a reference system available to any future civilization capable of calculating precession. Under this reading, monuments such as Giza, Nabta Playa, and Göbekli Tepe are messages across time. Their proposed meaning is not a prophecy naming a future people. It is a coordinate: the world has a clock, catastrophe marked a point in that cycle, use the sky to locate your own time. The builders could not know who would read it. The manuscript says we are simply the first civilization with the combined computational, archaeological, and interdisciplinary tools to attempt the reading. That creates what Chapter 18 calls the human variable. Ancient societies could not prevent the changes they remembered. Modern civilization possesses early warning networks, resilient infrastructure, agricultural science, and international coordination on a scale they could not imagine. The message, as the book presents it, has arrived. The cycle is readable. The preparation window is open. What modern institutions do with that message is the one variable the ancient builders could neither predict nor control. Chapter 19 draws the boundary between narrative and prediction. A framework that only explains the past can be illuminating, but if it cannot be wrong, it cannot be tested as science. The book therefore states 13 geographic, temporal, and observable predictions, along with conditions that would falsify them. They rest on 3 physical claims. First, the magnetic poles are moving, and the upper atmosphere's electromagnetic structures are organized around magnetic coordinates. The movement and direct electromagnetic organization are presented as confirmed science. Second, solar cycles modulate solar magnetospheric coupling. The direct coupling is established. The proposed geographic concentration of atmospheric consequences in the radius zones is the framework's extension. Third, Historical solar minimum effects appear, in the book's analysis, to concentrate around the magnetic pole's radius zones at those times. The historical pattern is the evidence assembled by the manuscript. Whether the radius mechanism caused that pattern is the central question the predictions test. That distinction governs the whole episode. Measurements are not inferences. Inferences are not predictions. Predictions are commitments to future observations. The manuscript does not present the 13 tests as certainty. It presents them as the point at which the framework accepts the possibility of being wrong. The predictions are stated. The test is coming. Predictions 1 through 3 test geography. Prediction 1 is the core test, during the next grand solar minimum, projected by the manuscript to peak around 2033 to 2038. The most severe agricultural disruption and growing season contraction should concentrate in northeastern China, Mongolia, northern Kazakhstan, and northern Russia rather than the northern European and North American regions most affected during earlier observed minimums. The book specifies measurable thresholds in Chinese growing seasons, Mongolian livestock mortality, and the relative severity of effects in Iceland and Scandinavia. Its falsification condition is equally direct. If Northern Europe and Northeastern North America suffer primary zone agricultural catastrophe while Northeastern China and Mongolia remain near baseline, the radius model fails its central geographic test. Prediction 2 says Australia's existing bilateral rainfall split will deepen, southern cool season rainfall declining while the northern monsoon intensifies, with stated thresholds during the 2033 to 2040 window. Prediction 3 concerns polar vortex geography. The manuscript predicts at least a 50% increase in deep East Asian sudden stratospheric warming intrusions relative to the 1980 to 2020 baseline, while comparable North American sector events decrease or remain stable. These are not loose statements that any outcome can satisfy. They specify regions, baselines, windows, magnitudes, and contrary observations. Geography is the trial. Predictions 4 through 7 move from geology to fields and farms. Prediction 4 says the Reykjanes eruption series will continue through at least 2030, that an Icelandic eruption of volcanic explosivity index 4 or greater will occur in the 2025 to 2045 period, and that seismic activity along the West Antarctic margin will measurably increase. The stated falsifiers include the eruption series ending without resumption, no qualifying Icelandic eruption despite continued ice loss, and Antarctic seismicity remaining at its earlier background rate. Prediction 5 says the South Atlantic anomaly will continue expanding and deepening through 2035, with its 32,000 nanotesla contour at least 15% larger than in 2020 and increasing satellite anomalies. Prediction 6 says Earth's average geomagnetic dipole moment will continue declining, reaching at least 18% below the 1840 baseline by 2040. Stabilization or recovery within 10% of that baseline through 2035 would falsify it. Prediction 7 says frost-free growing seasons in Heilongjiang, Jilin, and the Mongolian steppe will contract significantly during 2029 to 2040, exceeding what warming-only projections expect. Continued lengthening without departure from those projections would count against the claim. The tests cover different systems, but the manuscript binds them to one question: does the proposed mechanism generate the specific changes, in the specific places and times, that it says it should? Predictions 8 through 10 test connected oceanic and cryospheric signals. Prediction 8 says Indian Ocean dipole variability will increase, producing more extreme positive and negative phases than the 1980 to 2020 baseline. It also predicts at least one East African locust outbreak during 2028 to 2038 comparable to or larger than the 2019 to 2020 crisis. Stable dipole variability and no qualifying outbreak would falsify the stated prediction. Prediction 9 says Atlantic meridional overturning circulation transport will become more variable than in the 2004 to 2023 rapid array baseline, including at least one episode below 14 spheredrops during 2028 to 2040. Remaining inside the earlier variability range would falsify it. Prediction 10 concerns Greenland. The manuscript predicts that ice loss will remain concentrated in southeastern and northwestern coastal sectors rather than becoming statistically uniform around the ice sheet. Uniform circumferential redistribution as the pole continues moving would count against the proposed organization by pole position. These predictions show why the book insists on measurement rather than impression. A storm, a warm year, an eruption, or a single crop failure cannot prove the model. The specified baselines and distributions must be tested across time. The framework is not asking whether dramatic events occur. They always do. It is asking whether their frequency, geography, and correlation match the pattern it has committed itself to in advance. Predictions 11 through 13 complete the trial. Prediction 11 says cultivated area and agricultural production in northern Australia will expand during 2025 to 2040 while southern production contracts, deepening the continental split rather than producing a uniform national trend. Prediction 12 moves into political stability. Using consistent indices, the manuscript predicts deterioration in Mongolia, Kazakhstan, and Kyrgyzstan during 2030 to 2040 correlated with agricultural stress, and greater than deterioration in northern European countries moving away from their historical exposure. Stable or improving scores in those primary zone states while northern Europe deteriorates as much or more would falsify it. Prediction 13 is retrospective. It calls for a systematic comparison of Younger Dryas cooling onset with paleomagnetic pole reconstructions for 12,900 years before present. Spatial correlation with the proposed magnetic radius would support the model, no correlation would falsify this part of it. The critical window is approximately 2029 to 2045. Some data already accumulate. Other tests require the projected minimum to develop. The manuscript does not demand that all 13 produce a perfect verdict. Partial confirmation and partial failure would require refinement. But prediction 1 remains diagnostic. If disruption follows the rotated geography, the core claim survives its first major test. If the old geography is devastated while the new zones remain at baseline, the core radius model fails. The framework then asks science to investigate. It asks geophysicists to test the atmospheric consequences of changing magnetic pole position. It asks paleoclimatologists to compare Younger Dryas cooling maps with paleomagnetic reconstructions. It asks climate modelers to add a time-varying geomagnetic field and determine whether it improves regional forecasts. It asks archaeoastronomers to test whether monument reference dates converge beyond chance or independent symbolism. It asks agricultural scientists and risk modelers whether the radius zone variable improves long-range production forecasts. The manuscript presents these as extensions, not replacements. Greenhouse warming science explains rising global average temperature. The book proposes an additional variable for the geographic concentration of some effects. Solar science measures activity across multiple timescales. The book proposes a geographic model for where minimum period consequences concentrate. Climate conflict research documents correlations between environmental stress and disruption. The book proposes a reason particular societies were exposed in particular eras. If the predictions fail, science learns what magnetic pole position does not explain. If they succeed, science gains a variable that may improve geographic specificity. Either result is useful only if the tests are performed systematically and the evidence is allowed to revise the framework. The stakes, the manuscript concludes, justify the test. That is what science is for. The epilogue begins with honest accounting. The book separates its claims into three categories. Confirmed science includes measured pole migration, documented ice loss, geomagnetic field weakening, expansion of the South Atlantic anomaly, the reality of the Younger Dryas and African humid period, and established correlations between climate stress and civilizational disruption. Framework inference includes the proposed atmospheric organization by magnetic radius zones, the reading of monument alignments as a shared precessional reference, and the model's explanation of historical collapse geography. Prediction includes the 13 commitments to what should be observed during the next 2 decades. Confirmation of the central geographic reversal would not prove every mechanism or every historical interpretation. It would establish that an important effect is geographically organized and justify deeper work on the coupling pathway. Falsification would not erase pole movement, ice loss, atmospheric measurements, or climate collapse correlations. It would mean that the magnetic radius is not the organizing cause proposed by the book. The manuscript is unequivocal: if the projected minimum devastates the old primary geography while northeastern China and Mongolia remain at historical baseline, the radius model fails. A failed framework would still narrow the problem. The book says it would rather be falsified clearly than sustained ambiguously. That is its promise to science. The book ends where it began, Boothia Peninsula, June 1, 1831. James Clark Ross planted a flag and recorded a measurement, the magnetic North Pole at 70 degrees, 5 minutes north, 96 degrees, 46 minutes west. It was not a prophecy. It was a fact fixed to a day, a place, and the precision of his instruments. If that flag remained, the manuscript says, it would now stand roughly 2,200 kilometers from the pole it once marked. The ice is still at Boothia. The pole is not. What moved with it is the question this entire series has followed. The book acknowledges that its description may be wrong in important ways. Science advances through better descriptions, made testable in ways their predecessors were not. The next 2 decades will decide whether this framework earns a place in that progression. What civilization does before then is the human variable, whether it measures, tests, prepares, and builds resilience in the geography the model identifies, or whether the evidence demands a different map. The ancient message, in the manuscript's reading, says the world has a clock. Ross's measurement says the axis moves. The predictions now say where to look. The framework survives or falls on the evidence. The axis has always been hidden. It is hidden no longer.